So we'll start with just some basic announcements for the day, some information. One of the things I wanted to comment, I made a comment to some of you yesterday evening in planning the next conference. It's an important point that I don't think was covered well enough. I intended to do it during my introductory comments, is just to talk a little bit more about Barry Beck and his role, his influence on the conference. In the early 80s, there was not much known about sinkholes, and there was this separation of knowledge and information. You'd have geologists doing their things, you'd have the engineers doing their things, and the two parties, would rarely talk to each other unless someone forced them into a room. Barry's plan with this conference was to bring people together, to learn from each other. And so, as a result, he tried to schedule these conferences to keep them relatively small, to keep all the sessions plenary, so that everyone's in the room together learning from each other. Because he, as he told me a number of times, damn it, if I have concurrent sessions, the engineers are going to go there, the geologists are going to go there, and these people need to learn from each other and talk to each other. So, and he did that very successfully with the start of this conference series in 1984. Since then, we've seen just tremendous progress in terms of remediation, prediction, understanding, not just of sinkholes, but of a lot of karst phenomenon. In the 1980s and 90s, a number of conferences like this sprung up. This is the one that survived and has been the best attended internationally. We have people from 8 different countries attending this conference, and that's a low, because of COVID. Typically, we get anywhere from 12 to 14 different countries here. But because of COVID, we certainly were a little bit lower in that international count. So anyway, so I just wanted to say that to recognize just a little bit more of Barry's contribution, not just to the conference, but overall cave and karst science, management, engineering. An oversight on my part is, I know I wrote this up, I just didn't send it to the program, to Brian for the program, is a description of the panel discussion this afternoon. ASTM, if you're not familiar with ASTM, it is one of 2 international organizations that develop standards for just about everything. From testing the seat that you're sitting on to make sure it will hold you up, to now ASTM is developing standards involving karst. And so a karst subcommittee has been created in ASTM, and the purpose of this panel discussion is to start with some basic presentations to let you know what ASTM is what it's doing in the sense of karst, and then open it up for discussion so you can ask questions and recommend even if you're not able to get involved in ASTM, and we recognize everyone has limits on their time, but if you would really like to see a particular standard created, then we'll be glad to hear from you. Up at the registration table where I've been hanging out a lot, we've got also some brochures from ASTM. So if you want a little take home with you, please come by and just pick this up. As a reminder, if you didn't hear it all, the silent auction for the Beck Student Fund closes at 6 o'clock this evening, right after the panel discussion, the ASTM panel discussion. And so what that means is, don't go there at 6 o'clock and try to outbid someone. If you want to outbid somewhere, be there at 5:58. At 6 o'clock, we need to make all the sales, take care of all the paperwork, and then be back in here at 7 for the, for the banquet. And so one thing that some folks, I think, haven't noticed is that for several of the items, there is a buy now price. So if they put a price that says, if you pay $10, $100, whatever it is, that means you can buy it now. So I noticed at least, and I don't see the person who did it yet, probably wisely still asleep. But there's one person at least who's got a buy now price there. And when I see him, I'm going to say, come on, just take it with you. And that will make it easier for us come 6 o'clock, make the line shorter. So if there's something you really want, just pay that buy now price. There's a QR code to scan to pay, and then come and check out with me as well. For the banquet, we have 10. We're prepared for 10 vegan meals. So if you selected a vegan preference, then I'll coordinate with the caterers exactly how they're setting that up. I believe it's a buffet style that they're setting up, but we'll get you more information. So if you did not sign up for a vegan meal, don't go to the vegan meals. That's for those folks. One other thing is that there was a request, and this has happened at other conferences. If you would like to stay in contact with your fellow Sinkhole conference attendees, I'll pass around the list, and then I'll have it at the registration desk. Just add your name to the list, and what I'll do is I'll send the name of addresses, email addresses, and names to anyone who's on this list. Otherwise, NCRI does not share, for privacy reasons, does not share names and addresses with folks. But if you want to share share address with other folks who are here, I'll pass this around, and just add your name. That's all I've got. Are there any other announcements, thoughts, anything, questions, anything from the floor? Nope? Okay. And our first presentation, Dave, what time does our first presentation start? 4 minutes. Okay. Well, you don't need to look at me anymore.
Well, good morning, everyone. Okay.
We're going to start the session. This is the geophysical section you've all been waiting for. There have been teasers all week on geophysics, and now you're going to hear talks from some of the best practitioners in the industry. Oh, sorry. Standing in front of the camera. So this first talk is from Casey Albritton and Clint Kromhout, and we're looking forward to it.
All right, well, good morning again. My name is Casey Albritton. I'm a professional geologist with the Florida Geological Survey, and I'm going to share some work that we have done around Porter Hole Sink in Lake Jackson, Tallahassee, where we've done some geophysical work there. So this project came about because of the draining of the lake in Tallahassee. It's kind of a periodical thing that happens, and it's a karst lake, and so we wanted to go out there and try to use some near-surface geophysics to see if we could see anything in the subsurface that related to the karst activities that are in the lake bed. We wanted to see if we could see possible air-filled or water-filled voids, and so we wanted to go ahead and throw everything we had at it, our newly acquired seismic gear and our resistivity gear, and also do some GPR as well. And then try to ground truth all that with our hammer rig coring. And so I'll show you all the results of that. First things first, though, I'll show you a little bit of the regional geology in Tallahassee here. This lake is Lake Jackson. The red dot is the study area. And all of Florida is underlain by eogenetic limestone, very young limestone that dissolves easily. If you look at the map over here, the grays are the Miccosukee and Citronelle formation, and they're kind of capping the hills. And then you have the Hawthorne Group Terrea formation, which is its upper member is more siliciclastic, and the lower member is a little more carbonate rich. and that's kind of where all the karst lakes are sitting in the area in that. And then below that is the St. Mark's Formation, which is a fossiliferous limestone, and then below that is the Swanee limestone. And we used borehole 18025 to kind of corroborate with our other hammer rig samples, and it's right next to Porter Hole Sink. So on the left here is Lake Jackson with that blue dot representing Porter Hole Sink, and if you can see that faint blue line, that represents the high water line when the lake is full. So the picture is, that's when it's been drained. Over to the right there is the picture of Porter Hole. The actual opening is at the bottom here. You can see the upper terrea exposed right there, and the official, the lake sediments above that. The lake originally, before it was named Lake Jackson, was Okehipke, which meant disappearing waters, is an appropriate name. That's from the Mississippian culture. And it drains every 10 or so years, give or take. And it's driven by the potentiometric surface and the Floridan aquifer and by precipitation. And so on the right, you can see a close-up view of Porter Hole Sink, the study area. And if you look closely, you see there's a bunch of circular features everywhere. All those are karst related. And the area adjacent to Porter Hole right here is kind of where we wanted to focus. We have a little cluster of 3 sinkholes a little bit to the south of Porter Hole Sink. And we wanted to see if we could see any kind of connectivity between some of these things in the subsurface. So here's zooming in a little bit closer, and we're focusing on these sinks down here. Back in 2000, when this happened, when it opened up, back then we had some of the FGS staff climb down in there, and you can see this little kind of green squiggly is the area of the known cave passage under Porter Hole Sink. It's not a very extensively mapped cave. It could, and it covers a pretty small area just next to Porter Hole. So we wanted to see if we could see any extensions of this cave system in the adjacent areas. And so for our data collection, over here on the right is kind of a spread of all of our transects, and for future reference, when you see the data, they're all oriented south to north and west to east. I'll explain that as we're looking at it. We collected just one 250 megahertz GPR line, this purple line here, 5 ERT lines, which are the yellow lines, and the one orange line. All of them were 2 meters spaced with one longer roll along, and we did a 4 meter space roll along ERT. That's the orange line there. We did one MASW multi-channel analysis of surface waves right there, that green line, which is also the refraction tomography line, and that was using a 48 channel system for the refraction and then 24 active channels for the MASW with a shoot through roll along approach. And then we did the hammer rig boreholes for ground truthing the resistivity along this profile here and in between the sinks and further along that line. And so the results from the GPR, as was expected, we didn't get too much depth of penetration with the clay lake bed sediments. We got about 2 meters, but you could see that there was some expression of the underlying karst in the overlying sediments, and some of these other features where we had some signal attenuation. Seems like we'll see where that falls in with the resistivity later. But this was not unexpected based on the sediments at the site. So the first 2 resistivity lines were this one right here, right between these 2 features. That's this top one here, and we got this resistivity low about 8 to 10 meters below the surface right there, which was kind of interesting, and we figured, well, we wanted to target that with a borehole later. And then in resistivity line 2, is a little bit different, a little bit higher resistivities. We don't have this resistivity low down here in the middle, so we're not seeing that there, but we do see over towards the edge, which would be down here at the bottom, that we do have a resistivity low here, but we got to be careful of these edge effects. So can't trust that too much. Now this is looking at the IP from the same 2 lines, and then what's interesting about the transect 1 is in the spot where we see the low resistivity, we also see a little bit of some chargeability and moderate chargeability here, which would suggest that it's probably it's perhaps it's clay or some sediment, not just a water-filled void. And same with the bottom, we see looks like some chargeability associated with that zone in the beginning of transect 2. And then for transects 3 and 4, we see transects 3 running from west to east. Here we also tag the resistivity low in a similar depth in between those features. And then as you get closer to the sinkhole basin, you start seeing more influence of what would be the probably the water table or more saturated sediments. And then we can see here in transect 4, which is the closest to porterhole sink, we have some of the highest resistivities at depth, which would probably coincide with the carbonate mudstone that we're seeing of the lower terrea at the site. And we're getting some very low resistivities above that associated with the water that's seeping through the side here, and it's actually seeping out into porterhole, and kind of this whole side of the sink is slumping and failing. So we're seeing good correlation with that. And then this is the IP from both of those. Basically seeing good correlation with very low chargeability and lots of water in the subsurface, very saturated, and perhaps a little bit of chargeability from some clays in the near surface or other artifacts. And this is the most important transect because we have it match up with our boreholes, and this is where we tagged the low resistivity from transect 1. We see it again in transect 5 right here, and then towards the end we see another low resistivity anomaly that we wanted to go ahead and try to tag there. And then this higher resistivity spot in the middle, we went ahead and put a borehole there as well. And then these are the results from the 4-meter roll along, get much deeper penetration or depth of investigation, and we're seeing this similar saturated layer, and then we're getting down here probably to the top of the terrea, weathered limestone, and this interesting feature at depth that could be related to some karst, maybe some karst infill, and perhaps we're looking at some extension of the cave that's infilled by sediments or water. Seismic results. So on top we have the multi-channel analysis of surface waves, and the bottom is the seismic refraction tomography, and just have a little black line showing kind of the inset of where the MSW fits within the refraction spacing. And so we get pretty good correlation between the two different methods. We're seeing some low velocity features at the surface that kind of have the same geometry, and then we get a kind of a moderate increase in velocity, and below that a little bit less higher or lower velocity values. We're seeing kind of a deeper to the north side of this, a little bit deeper infill of these moderate velocities. And so pretty good correlation there. Our shot points for the refraction, we're a little clustered to one side. Down on the southern end, it was completely saturated off the end down here, so it was hard to hit a sledgehammer, get a good signal there. The ground truth results here we have on the far left, we have the borehole that was drilled back in 2000, showing the undifferentiated sediments on top, followed by the terrea formation here. And what we're seeing line up with our hammer rig boreholes, we're seeing these pretty much reworked probably sediments from the lake that have fallen in with karst. We only tagged the terrea formation in this furthest south borehole, which was target hole number 5, and it was it wasn't the deepest borehole, so this borehole just next to it that went a couple meters deeper, we did not tag the terrea formation in that. So we're probably it's probably an undulatory surface that's, running somewhere through here in this, low to moderately low resistivity area, and probably not getting to our more indurated limestones till just a little bit below those depths. And in the chargeability, we can see that there's low chargeability over here associated with what we're seeing in the sediments, where we're seeing, we haven't seen any limestone in here. We're seeing sands, and we encountered a lot of flowing sands during the drilling process. And so we would hit in some of these lower resistivity areas. We would get a lot of I was expecting, based on resistivity, some clay, but it was actually just sands with tons of water in it, and we weren't tagging any just pure clays. This high resistivity in the middle of the line was actually clay-rich sand, still less than 10% clay, but it clogged up the hammer rig, and we had to extrude a piece of the material out, and it came out like a brick. And so that was pretty interesting. So the methods appear to correlate pretty well. We have the GPR up here, even though we get 2 meters. It seems like we get this piece right here where we have the signal attenuation lines up well with where we have the most clay in our resistivity line, and the seismic seem to line up pretty well with some of the velocities in there. And with the notable decrease in the resistivity, it's just below the surface here, and that's we're calling that the water table. These low resistivity, low velocity zones between the sinks and then the other transects are interpreted as saturated zones within high porosity and permeability, and they hold and transmit water better than these slightly clayier sediments around at similar depths. And then in transect 5 that we use to correlate to the test hole sample locations, we see that there's highly variable lithology at short lateral distances, which makes sense in karst. And then transect 6 suggests the potential for sediment or water-filled voids. So we didn't find indisputable evidence of conduits in the subsurface, but we are seeing what we're interpreting as permeable zones and the karst at depth and its effect on the overburden. So what we've done since then is we've run a line straight across Porter Hole, really just off to the south of it, and here's the depression that's Porter Hole, and what we're seeing is these high resistivities here. They're probably the lower Terrea formation mudstones and limestones, and we're seeing a potential connectivity of fluids and or sediment that are funneling down into the karst. And it seems that the IP is potentially supporting that idea. This slope right here there's water just kind of seeping out of it. It looks like there's a potential pathway here with some lower chargeability features. And so we just kind of plotted this in 3D space for fun. Here's the 2 sinks that we ran a couple lines through. We had the nice correlation with low resistivity below those. This is Porter Hole over here. We can see this vertical feature going in there, and based on the cave maps, that matches pretty well with a feature that's like that there. So in the future, we plan on targeting some of these deeper anomalous zones, get a bigger rig out there. Hopefully we don't open up a sinkhole under the rig. When we want to increase the quantity of the resistivity lines and the seismic, so we can do proper grid out there and try to do some 3D work. So yeah, thanks for everyone for helping, and I'll take any questions.
Hey, Casey, good presentation, man. Couple of questions. So the GPR profile, it looked to me that you had some pretty obvious, I guess, anomalies where you see the GPR have a localized increase in depth of penetration there. You called it out as underlying karst and potential effect of the overlying soils, probably some raveling zones, things like that. And apologize if I missed that, but did you put any borings at any of those locations, and what did you see in the behavior of the drill rig? Did you see, was it easier drilling? Did you, and I don't know if I could see that. Did you take like N values or anything like that, or what can you say about that?
Right. So for the drilling and the sampling, we targeted 2 areas that matched up pretty well with let's see, the southern end of that GPR line where you saw some of those slumping features, and that was just in the first 2 meters. And so we saw a lot of basically just convoluted hummocky bedding and a lot of organics in that first 2 meters. I didn't take like blow counts or those kind of things there. We were just getting samples real quick and just making notes of when we encountered flow sands which was a lot more than I expected.
Cool. Thanks.
Mm-hmm.
Hi, Casey. Thank you. You guys use IP a lot associated with your resistivity, it looks like. And I was wondering, have you found the IP data to be effective in helping distinguish, say, a water-filled cavity versus a clay-filled cavity?
Yeah, I think I'm still trying to, collect enough data to try to hammer that out. I think I think it's a convoluted thing because the water, if the water's got a lot of dissolved solids in it or something, you could probably get a similar chargeability to a clay or something. So yeah, it's I think more data to kind of have a spectrum of ideas on that.
Yeah, I'm glad you're doing it because that's really a tough target to figure out. And not too many people, our company included, we usually don't do the IP associated with the standard ERT. So I'm glad you're pushing it.
Thanks.
Our next speaker is Heidi Harwick, and she has 3 other co-authors, so I don't want to mispronounce their names.
Hi everyone. For those of you I didn't speak to already, my name's Heidi. I just started working as an environmental geologist with Robert Kistner in San Antonio, Texas. I just graduated last year from the University of Texas at San Antonio. My graduate committee and my co-authors are Dr. Gao, who some of you are probably familiar with, Blake Weissling, and then Alexis Godet. So big thanks to them for helping out with this project. There it goes. Anyway, so this is my master's thesis research project. I wanted to do an integrated study because I had read some papers about integrating hydrologic or geologic methods with geophysics, and I thought that was a really cool idea. So what I did was study the geology of the UTSA campus using near-surface geophysical methods, traditional geology, and then integrating that in GIS. So the kind of end products of this research were to create a revised geologic map using geology and GIS, and then using geophysical data to help update that map, and then putting everything together, including well data, and into a 3D model, which I thought would be a really cool way to visualize and analyze the data. And then the goal of this research was to look at the structural geology underlying the campus and how that influenced groundwater flow paths. So controls such as faults and fractures, stratigraphy, and how that water was going from the surface and recharging into the aquifer. So a little bit about the Edwards Aquifer. Jennifer talked a little bit about this yesterday. So the Edwards Aquifer is in south central Texas. It's about 180 miles long. It extends from Brackettville on the west up to almost to Austin, and then San Antonio is on the bottom right there. I don't know why I'm pointing. Anyway, so it's one of the largest and most productive karst aquifers in the United States. It's designated as a sole source aquifer and provides water for over 2 million people in the San Antonio area. And among some of the things it provides water for are species for endangered, or habitats for endangered species like salamanders and invertebrates. So the 3 main zones, you've got the contributing zone here in green, and then the recharge zone is the unconfined portion of the aquifer. That's where those Edwards rocks are outcropped at the surface. And then the dark blue is the artesian zone, or the confined portion of the aquifer. And then this is kind of a cartoon of how the faulting in this area has affected the aquifer. So there's a lot of offset and heterogeneity in the Edwards Aquifer, which makes it a little more complicated. So a little background on the Edwards geology. So the major structural features, you've got the Edwards Plateau, kind of like the hill country area, the Gulf Coastal Plain, and then the San Marcos Arch is kind of here. And then the Balcones Fault Zone is the major structural feature here. That formed in this sort of shaded area here over the buried Ouachita Mountains, where that former orogeny was. And that separates the coastal plain from the Edwards Plateau. And that's a series of high angle and echelon normal faults. And the faulting is thought to have primarily occurred during the Miocene. And that faulting has resulted in a lot of complex structure. So not only do you have all those high angle normal faults, there are cross faults, there's Horsten Grabens, and then all the associated fracturing. And there's also some relay ramps, including one in San Antonio, San Marcos, and there's like a couple other ones. So that was something I was looking for when I was looking at the structure of my study area. These rocks formed during the Lower Cretaceous. There's 3 trends: Devil's River, Maverick Basin, and then the San Marcos trend. So that's what San Antonio has. And those formed on the Comanche Shelf. This is kind of a cool little graphic I found. So that's a broad, flat, submerged back reef platform formed over a variety of tidal environments. So that resulted in a series of carbonates ranging from mudstone to grainstone. There's some boundstone. There's evaporites, marl, and then you even get some chert and some iron oxide and things. So it's a pretty interesting set of rocks. This is a modified stratigraphic column that I adjusted for Bexar County and the study area based on literature and then what I found during my research. And then the highlighted formations are those that were mapped at the surface in my study area. So the Edwards rocks themselves are the Edwards group, and then the Georgetown Formation gets included at the top there. So you've got the Person Formation on the upper part of the Edwards, and then the underlying Keener Formation. And then those are further subdivided into the members, and then the regional dense member kind of separates the upper from the lower. For your upper confining unit, that's the Austin Chalk, the Eagleford, and then the Buda Limestone and the Del Rio Clay, so that's your Aquitard. And then the Glen Rose Formation is your lower confining unit. The members that I mentioned, so each of these, the Georgetown Formation and each little member of the Edwards, those correspond to hydrostratigraphic units that are characterized by their porosity and permeability characteristics. And then the bold ones, HSU3, the Leachton Collapsed, and the Kirchberg Evaporate member, those are considered to be the primary water-bearing members because they have relatively high porosity and permeability. I think it's like 20%, and they are kind of the main water. I just said that. Anyway, but one thing that's important about these rocks is they underwent continental uplift, subaerial exposure, and then karstification. So a diagenesis occurred, and the aquifer formed, and that resulted in a lot of complex porosity and permeability. So you've got a triple porosity that includes the matrix, the fractures, and the karst conduits. And then those fractures can also interconnect zones of differing porosity. The groundwater flow in the Edwards. So the primary recharge, almost all of it, is where water flows over fractured stream beds in the recharge zone. So this is from my study area, and you can see these are quite fractured, and then the vegetation has been able to grow up through there. So as the water crosses those streams, that's where there's loss into the aquifer. There's also point recharge through caves and sinkholes and other karst features. There's also a lot of solution-enhanced fractures. And then the remainder is like when you get precipitation or overland flow, and then there's even a little bit that comes up from the underlying glen rows. In the contributing zone, as I mentioned, you'll get the overland flow, and then it eventually flows down the creeks and recharges. And then once it's in the aquifer, it follows the regional flow to the southeast, and then flows towards discharge points like Canal Springs and San Marcos Springs, which are up toward the east-ish, depending on where you are. As I mentioned, the faults have a big part to play in groundwater flow because they compartmentalize the aquifer and create a lot of local differences. So you can have flow along faults, across faults in some cases, and then relay ramps are a really key feature in the Balcony fault zone, and they are common in extensional environments where you'll get two parallel faults, and then a ramp will form between the footwall and the hanging wall, so the water can flow around and down, and this is also usually quite fractured, so that allows for diffuse flow, and then so you can have vertical flow around, and there's a lot of high transmissivity flow pathway, is what I'm trying to say. So those are pretty interesting. And this is actually an illustration of the San Antonio relay ramp. So a little bit about my actual project. As I mentioned, I did this on the UTSA campus. So that's located in Bexar County in northwest San Antonio. So here's Loop 1604 and I-10's over here. And then this is the campus outlined in red. This is also, it's about a square mile, so it's not huge, but when you're walking across it, feels bigger. And then it's part of the Leon Creek watershed, so you've got a creek that flows north to south here, and there's another one in this wooded area in the east, and then those join up with Leon Creek to the south. And then as I mentioned, this is in the recharge zone, but once I started working on the project, I realized not only it is in the recharge zone, which is this orange area, so the north and west portions of the campus are recharge zone where the Edwards rocks are outcropped. But the southwest portion is in kind of a special area. It's called a contributing zone within the transition zone. And that's where you have rocks that are younger than the Edwards, specifically the Buda limestone, and they're at a higher elevation. So that recharges by overland flow. So basically it flows into the creek, and then that crosses the recharge zone and contributes recharge that way. So I chose this as a case study, partly because it was really, really convenient to do research on the campus where I was already going to school. And this is a project that was suggested by my graduate advisor, Blake Weissling. But it is a really cool area. You've got we thought there was maybe a relay ramp. You've got a couple of faults. The published maps didn't agree where exactly those faults were, which is part of the reason I wanted to do a revised map. But generally, there was thought to be kind of a north fault and kind of a south fault that trended northeast across the campus. So I was looking for that, and then that kind of unique scenario of recharge and contributing zone in the same area. So I wanted to look at what the water was doing between the surface and the aquifer. So for my research methods, as I said, I did an integrated study. From what I've read, the integrated methods provide a more comprehensive site assessment because you're not relying solely on geology or solely on geophysics, and it gives you more data to look at together. It helps reduce some ambiguity. So like I said, I did look at the published geologic maps, and because they were all different, I ended up georeferencing and digitizing them in ArcGIS. And then I went out and collected my own field data. I also utilized GPS to collect data points, especially for the wooded area where it's really hard to kind of tell where you are. So that was helpful when I pulled all of that into ArcGIS Pro. For the near-surface geophysical methods, I did use 3. So I used electrical resistivity with a dipole-dipole array, and I also used EM31 and EM34 as well as ground-penetrating radar. I wanted to use seismic, but primarily the issue was noise because we had 2 major highways and it was a campus. So that allowed me to get some good geophysical data to go along with the surface geology. I also had 3 wells near the perimeter of the study area, so that helped verify the formations I was seeing at the surface and with the interpretation of the geophysical profiles. So I put everything all together into ArcGIS Pro for the surface geology. I also had a digital elevation model, 1 meter resolution based on LiDAR. So that was really helpful when I was creating my geologic map. And put everything together in a 3D geologic model. So that was kind of the thing that I was like, oh, this would be really cool. And it's a software called Move. It's usually used for structural geology. So I'll show you that later. So this is where I did my geophysical profiles. So it's a campus, so a lot of it is developed, and I couldn't punch holes or clear all the brush. And this is actually a critical habitat unit, so I couldn't be too destructive there. But basically, I did a bunch of GPR in the paved areas, so parking lots, roads, and that allowed me to get coverage of areas where I couldn't do resistivity. Part of the consideration with resistivity is obviously that you want a long enough line to get depth with good resolution, and then it needs to be somewhat straight line. And then a lot of places I did both resistivity and electromagnetic together so that I could at least compare the results. And then if I had an area like here or here where I could only do electromagnetic, I could at least kind of compare the responses I was getting, like, oh, okay, this is limestone, this is Del Rio clay, this is probably what's going on. So I used Earth Imager to do 2D profiles. I found those to be the most helpful. Honestly, if I had to do it again, I'd probably just do resistivity and skip the other two methods. And then I was able to import those profiles into cross sections that I incorporated into my 3D model, which was pretty cool and helpful in kind of cross-checking my assumptions for the model. For the EM, still kind of helpful. You get that profile with average bulk conductivity. Mostly, you can just see the transition between clay and limestone. The GPR was helpful. I mean, there was a lot of places where I couldn't do resistivity or another method, and the asphalt surfaces are really good because they've graded them so you don't have those clay soils attenuating your signal. So I got down to about 2.5, 3 meters, and you can see some shallow structural features, like if there's a little bit of dip or a little bit of an anticline, and some of the shallow karst voids as well. So that allowed me to see transitions between clay and limestone again. In general, I mean, as you'd expect, the Del Rio clay had really low resistivity, high conductivity. The limestones were pretty variable, whereas the Edwards had slightly higher high end of resistivity. And then the Georgetown had a little bit higher conductivity, which was helpful when I was looking at the EM profiles. So this is a little bit of a preview of my 3D model. So this is the map that I came up with. I think when you do geologic maps, you've got different people at different times at different scales, and it's kind of an evolving interpretation. And then mine was also very localized, as opposed to like a quadrangle or the whole aquifer. So it's kind of got 4 fault blocks with 3 faults. So I called this the North Fault and this the South Fault. This I determined that this is the Person Formation. And this is the cyclic and marine member here with a horst of leached and collapsed member. And the bottom here, we've got that upper confining unit rock, so the Butte limestone. And then the Del Rio is exposed really well in this creek that flows north to south. And then the really interesting part is this central block. This is the relay ramp. So I was able to confirm that, yes, there is a relay ramp here. So as you go to the southwest, it goes up the stratigraphic section from the cyclic and marine member, through the Georgetown, which is thin, that's why it's just a little bit, and then Del Rio and Butte. So that was a pretty cool finding, and I used the digital elevation model to help with the contacts. So, and then these yellow dots are the karst features. So as you can see, these are all in the Person Formation, except this is just a little solution-enhanced fracture zone. So you've got caves here, and there's one here, and there's one down here, and then the rest are sinkholes. And those have some varying dimensions and depths, but they are point recharge features, and so you've got those in this Person Formation that are contributing to recharge. So these are my electrical resistivity surveys. I won't go into too much detail or we'll be here all day, but basically we've got elevation on the left, and then the higher resistivity is in red, so there's Butte, and then the lower resistivity is in blue. So for example, this line was over in that contributing zone. So you got a little bit of Butte, a thick layer of Del Rio, and then the Georgetown and the Edwards below. Line X was kind of interesting because I was trying to catch the southern fault here, but you can just barely see the edge of the fault zone where there's maybe some dissolution or some fracturing. And then the Edwards there is quite resistive. Line W was actually really interesting. Again, I was trying to catch the fault, but I didn't. However, this was still really helpful because it helped me confirm that yes, the relay ramp is here and that the elevation of the top of the Del Rio clay was deeper than it would have been if it was just topography. So you've got a little bit of view to there. But the other interesting thing is that the Del Rio is much thinner on that part of campus than it is on the southeast part. So another interesting thing there. And then line Z goes across this creek, and that helps map that north fault. So you've got really resistive Edwards there, and then sort of a bending structure that I assume to be part of the relay ramp. This part was really interesting. So this is the northeast section of campus, and as you can see, there's kind of a lot going on here. So I'll try to explain it well. I think one of the things I want to point out is these drag folds in lines A, B, and C. So you've got these more resistive areas that are tilting to the south, and those are kind of sandwiched by clay or less resistive material. So that's on that hanging wall of the southern fault here. The other thing is the Del Rio clay is a little bit deformed on the hanging wall. Line E was kind of interesting, so that's here where it crosses this fault. So as I mentioned, the Balcony fault zone is typically high angle faults, high angle normal faults, but here it's really shallow, so I figured it was maybe just a series of step faults, and you can kind of see it there. So that results in that being a shallower fault plane. What else? So the other thing that was interesting is I've got more tilting here in line A, so that's this one that goes along the eastern edge. So this is the Horst, and then this is the east end of the relay ramp. So those are tilting to the north, which I was not expecting, because when you learn in school, you're like, oh, it just shifts, but it wasn't. And then this is a pretty dry area. The groundwater in the unconfined portion is about 100 feet below the ground surface, if I remember correctly. So I interpreted this area to possibly be a cave, an air-filled cave, and then this is potentially a clay-filled void, as is here and here. So a lot of interesting kind of karst features are going on in this area here. So it was really interesting to interpret these sections because I had to ask for a little help because I was like, wow, this isn't just layer cake geology. So it was pretty exciting to see those results in the profiles. So this is my 3D model. This is a software that I learned as part of an independent study project to import 3D seismic data. Then you can create horizons. And I was like, hey, this would be really cool to use in my thesis. So it's made by petroleum experts, and Midland Valley provided the license to UTSA so that I could use it, which is great. I think I used 3 vertical exaggeration. So here's the digital elevation model, which I did have to fold due to the size. And the fault planes are here in red. And then I draped the surface geology over the top. I mean, as you can see, I didn't do it quite perfectly. But you can kind of see, like, oh, hey, here's how everything comes together. And then the top of each member is represented by a colored plane. So you've got the Caner Formation in pink, the Person Formation in blue, Georgetown, and then Del Rio and Dyer in brown. So this one is sliced into the model, so we're still looking to the north, but I thought this was a really cool way to highlight the relay ramp. So you can really see that tilting to the southwest, and this also highlights how you get the different exposures at the surface and the offset between either side of the fault. So for example, here between the south fault plane, you've got those upper confining units with clay right next to the more permeable Edwards. So that might be a place where you don't have cross-fault flow. But further down, if you've got water infiltrating in here and it's slowing down the ramp, it can either go along or maybe along the fault plane once it's here in that permeable part of the Person Formation, specifically the leach and collapse member. Now you do have a less permeable member. This is the regional dense member. That's probably not going to float down, but you've got the fault plane there, and then it can get into the Caner. So there's certainly potential for multiple groundwater flow paths, including cross-fault flow, as well as down and around. And you can see a little bit of the offset between here and here, but let me go to my next slide. This was kind of the cool part of the model, I thought. This is that northeast part of campus, so we're looking to the northeast. So you've got that north block. Oh dear. Okay, anyway, so there's a north block here, And then that horst with the leaching collapse member on the surface, this is the east part of the relay ramp, and then there's that south block with the upper confining units here. So I thought this was a really cool visualization of how you have both vertical and lateral flow paths. And keep in mind, these are all quite fractured, especially in the vicinity of the faults. And you've got karst features, so there's potential for water to infiltrate via point recharge into the person formation, go along these faults, flow down the relay ramp. So, I mean, it's definitely a qualitative model, but I did use as much quantitative data as possible. And I thought this was a really cool way to visualize my data. So I hope that you found it interesting. So just to kind of wrap up, I did kind of meet a lot of my goals on this. I did confirm that there was a relay ramp. I was able to define the locations of the faults a little more specifically instead of just, oh, there's a couple that cross the campus. There were some differing interpretations on the surface geology, so I feel that mine made sense for what I observed in the field and based on the well logs. And then getting a better idea of the groundwater flow paths. So while this is just a small square mile area within the entire Edwards Aquifer, I mean, hopefully this will help provide some information on how localized flow might act and then might recharge into the aquifer and kind of add to that database of knowledge that we have for the Edwards. I thought this was a good case study. I might be a little biased, but I think it was interesting to be able to incorporate so many elements. You know, geophysics is great, especially if you have more than one method. Geology is great, but you're really only looking at the surface. So putting those together and then using GIS and this 3D model as a vehicle, I thought was a really cool way to look at the data in a very, very visual way and think about those relationships in a way that where you can kind of slice through the model instead of just, oh, let me sketch a cross section, which is, fine. But the 3D model I would definitely recommend if you're looking for a cool way to visualize your data. So anyway, that's all I have. I do want to give thanks to the Society of Exploration Geophysicists for the Near Surface Geophysics Award that I got last year that helped to fund this research. And then, of course, the Beck Student Support Foundation, my graduate committee, and a lot of other people. I mean, I was really impressed by how many people were willing to help me out and answer questions while I was a student and now as well. So that's all I have. Thanks. I forgot to put my contact info on there, so let me know if you have any questions.
I have just an observation here. That's a really impressive presentation. I very rarely see anybody doing resistivity surveys in an area where that's structurally complex like that.
Oh, thank you.
Yeah, but I noticed. Did I miss your discussion of the GPR and EM?
I didn't really talk about it, just in the interest of time. I do have several slides in which I can show you, but GPR I thought was helpful, even though it was just that upper 3 meters. And there were places, let me see if I can. For example, I did a line along here, and when I was talking about those tilted beds, you can see that in the GPR. So there's a tilting near that hanging wall. I also did one in this parking lot, and there was a little anticline. So I mean, I did want to include pictures of that, but it's a 20-minute presentation. So,
yeah, so you had a 3-meter exploration depth with GPR?
Yes, I think it's because, and this is my advisor recommended it, because the asphalt parking lots and roads had been graded, then you don't have those clay soils attenuating the signal. So I think at least 2.5 to 3 meters. So I actually got deeper than I expected. And,
yeah, what's your survey depth on the ER there? I can't quite see the
well, the spacing was variable. I did between 3 and 5 meter spacing, so 30 to 50 meters on average. Yeah, so pretty good. Yeah. My longest line was actually this one. I did 6 meter spacing on that one, so that one got down 60 meters or so. So not bad, and I thought it turned out okay.
I had a conversation last year with a geophysical consultant who made the sweeping observation that something like 75% of the continental United States is not suited for GPR surveys.
Well,
I believe alcohol was involved in that conversation.
You know, those clay soils don't make it easy, so.
Yeah, that was a fantastic presentation. Congratulations. I mean, you sure got a PhD for all that.
I'll tell UTSA.
Did you find the EM to be of any value in finding that transition across the fault zones? And if you did, 31 versus 34 data?
That is a good question. I don't want to say it wasn't useful. I just think it was less useful than the GPR. So I did EM34, I think, here, and here, and then here. And you know how EM31, you get down to maybe 6 meters with vertical dipole. EM34, you can get down to maybe 30 with vertical dipole. So it then ends up, oops, wrong way. So like on this one. So you get, when you do your EM31 profile, you can see like, oh, okay, I've got low conductivity here where I'm crossing this little bit of Edwards, and then there's higher conductivity because there's clay in the fault zone. And then more here where this Del Rio clay is exposed in the creek bed, and then it goes low again here. And then the EM34 was actually kind of cool to see because those transitions between low and high conductivity shifted over to the right because you've got this more resistive, less conductive Edwards, and then the clay, and then it sort of changes it over here. So I think it was helpful where I couldn't do resistivity because, you know, it was the campus, so they don't really let you drill holes and clear a bunch of brush. So I think there was a couple of lines where I couldn't do that, and I was like, oh, okay, this is a transition between those rock types, though I probably would have skipped it. However, it was a good academic exercise to kind of see its usefulness and limitations. Does that answer your question? Sorry.
It does. And on the GPR, you used the 400 megahertz antenna. Was that just because what you had?
That's what the school had.
Okay.
Yeah.
Yeah, I'm wondering if their new 200 would have done a little bit better for you.
I think that would have been really cool because we could have gotten deeper. I mean, the resolution's a little lower with that frequency, but I think it would have been good enough to maybe see some deeper features, especially where I saw some of those shallower structural features. It might have shown more deeper. So, I mean, maybe for the next student, they can rent an antenna or, you know, the school can get some new gear, but that was one of the things that I considered is like, what do we have that I can use? So, yeah.
Thank you.
One of your maps has sinkholes on it.
Wrong way. This one.
Yeah. Are those along the stream beds, and do any of them act as stream sinks when you get transitional water flows across it?
I tried to find a pattern, and I did look at fractures when I was doing my geologic mapping, and they are basically in the same trend as the regional faulting with some conjugate direction as well. I've seen theories that a lot of these occur at intersections of fractures and faults, so I think a lot of those are explained here. These two caves are right next to that fault, so those are certainly connected to fracturing, I think. But here, there's not really anything there, and there's no spring. Like, that's a cave, but I don't know why it's there. And then here, this is where that creek flows, so I think the cave's there. But so I think there's certainly some hydraulic connection, but I just don't have any way to prove it. In my thesis, I was like, hey, you know what would be a really good project for somebody is to study these and see if they're hydrology connected.
Are they cover collapse sinkholes? Or are they actual sinkholes into the bedrock?
I think they're I don't think they're collapse. I think they're from dissolution. I don't know for sure. Basically, basically it'll dissolve, and then once it hits like the regional dense member, it'll kind of flow laterally across the bedding planes until it finds like a fracture. So I think they're dissolution versus a collapse. I honestly don't know as much as I should about them.
Yeah, first, just a comment that Move software was very impressive. I thought it was a very creative use of that. Very interesting to look at. So kind of a curiosity question. I know you used some existing wells for reference for your interpretations. If you were to choose a handful of locations to put some borings in, where would you put them?
That is a good question. So the wells, there was one here, one over here, and one here. So I would definitely want one maybe here so that you could dig through So you could see the transition from that upper confining unit through the Georgetown and into the person. I think kind of in each fault block, basically. I would want a couple in the central area to help correlate that fault relay ramp, and then at least one in each fault block, I think would be good. But that's one of those things where I'm still learning how borings work, and I would have loved to do that and maybe have done a little more work trying to contact companies who've maybe done geologic assessments out there and be like, hey, did you do any borings? Can I have your information? But hindsight,
No, sure. Thank you for that answer. I think it would be interesting to put it where you called out some of those air-filled or clay-filled voids.
Like up here?
Or tunnels. Here? Yeah, that would have been interesting to truth. Yeah.
That would be really cool to confirm if it's air or void, or if it's clay, or if it's just epikarst or something.
Right.
So.
Thank you.
Yeah, thanks.
Do we have time for one more question?
The next speaker is me.
Thanks, everybody.
Thank you, Heidi. Next speaker is me. So. That's part of that aggressive marketing I'm known for. Okay. All right. I'm Peter Hutchinson, obviously. Alex was the crew chairman for this project, and Kate did the processing. Kate is the VP of the company right now. And we're going to look at something different. You've seen the last few days all these different projects, but I think these two this morning were excellent in showing multiple use of geophysics to help answer questions, and that's that's probably the best thing about those two talks, is that they used all these different pieces of equipment to show what was going on in the subsurface. This particular talk, we've been I don't know how many we've done, maybe 30 or 40 of these huge solar farms, PV, photoelectric, and all these different things. And the problem is you can't use sounding methods. Sounding methods being something like gravity or EI or any one of the ones that you have to put something in the ground. You can't cover hundreds of acres and do something like this. So our clients have asked us to help them out in some way. One of the ways is what we call, profiling. That's what we call it. It's not a sounding tool, but it does collect sounding data. It's just that you're moving all the time and collecting data all the time, and the data is correlated with, the global positioning system of the thing. And to reiterate, geophysics is tertiary data. I know engineers want to know down to the 10th decimal place, but it is tertiary data. Primary data being an outcrop, secondary data being a boring or a pit, but it's tertiary data. So it helps you understand what's going on, but it's not the last answer. It's the beginning of the answer. And in this particular situation, they were looking for karst features and rock, and pretty much all of these that we've done. And one of the most common tools for looking for karst, as you've seen, is either EI or seismic. But I want to throw in frequency domain, which is a question a couple of people have asked. And the particular one we're looking at is just using frequency domain terrain conductivity mapping. And the big problem with that is that it measures bulk conductivity. So you have no vertical acuity. You don't know where things are happening, and that's really a problem with that tool. But people have gone through and figured out and written programs to integrate these multi-dipole tools. And I think Geonyx now has one. The one we use is out of a Czech company. And they give you bulk conductivity in several different zones. So, let's look at the advantages real quick. The big advantage is the fact that it goes quick. You can collect a lot of data fast. So when you're covering, literally hundreds of acres, you can move pretty fast and collect a lot of data. If you were doing EI profiles, it would take you the rest of your life to look at a site. They're easy to set up. The collection is fast and it's processing straightforward. If you integrate with a UTV, you can really move. This is one of the tools we use. I think we've got 4 of these. This tool is, trying to remember how long it was. I think it's 16 feet long, but it might be 18 feet long. And it is a 3-dipole unit. And we've been using that for imaging top of rock and potentially where karst features are located. Here we have an EM31 attached to the front of the vehicle. We've pulled them and we put them on the front. We found putting them on the front works a little better for us. When you have them on back, they rock. If you put wheels on the ends, then you can't take a turn. You have to get out and pick it up and move it to make a turn. So putting it on a vehicle like this, and you'll see another example. But there's disadvantages with this tool, and the big disadvantage is that it's just bulk conductivity. It tells you the conductivity in a zone, in a range that's usually, it's about 1.5 times the dipole distance. And it saturates near metal. As you can see from looking at that, it's awkward to deploy. You can't use it around forests, tall plants, things like this. Out in the field in Texas, I was doing this, and I thought I could go through a plant that was this tall. It was an iron plant of some sort. It didn't move. That did. So in a single dipole situation, you really don't know how deep it is. This picture, by the way, was taken well before the Marcellus Shale salt basin was put in, so that's why they look a little different. But the basin was there, and it was leaking, and they saw it up here leaking out, so they asked us to come out there and figure out where else the contamination was. And you can see it's just a rim around there where it's hit some sand, and it's popping out. So, but we have no vertical acuity. We don't know where it sits in there. We just know where we can see it at the edge, where it popped out. And for those that aren't familiar with the tool, it has a transmitting coil. It hits a surface conductor of some sort, induces a secondary magnetic field, eddy current we call it, and it's picked up by the receiver. So there's a guy holding the tool. But now we look here, we can see that if we put 3 dipole units, we can get 3 depth ranges. And if we, and here, by the way, is that tool deployed. And you're saying, well, don't you have some interference? Most of these UTVs are plastic in the front. So that tool is 14 feet away, even though it doesn't look it on there. It's 14 feet away from the tool. But there is some interference. We know that. But since it's collected everywhere, that interference is blended out. So if there's something happening in the subsurface, we'll see it, even though there's slight interference from the thing. That's a 3-dipole tool. Oh yeah, I had some stuff on that. But so the first thing to do in this processing is you got to get rid of the negative data, and that's easy enough to do. You go through a spreadsheet, you have your X, Y, and Z values, and you just delete the ones that are negative, and then you smooth the data, and you can see we've got dipole 1, 2, and 3 up there. The final processing, and then we convert. Now, this part, we bought this program, and the way they do their algorithm is they want it converted to resistivity. Why they did it? This was their answer. They thought it was mathematically easier. There's really no point in doing it. You can do it either way, but this convert it to resistivity. And so now you have this is, these 3 data points, and you can then process this out, do forward modeling and produce, like in this example, we did a 15-layer model. Sometimes we do a 12-layer model. What we're trying to find out is where the break is between the overlying soil. In the project I'm going to show you, there is glacial soil on top of it. And so now we're going to look at the project, now that we've gone through all the processing. I had to tell you that because a lot of people are very negative on EM. I understand why. It has some uses. You want to find a drum under the ground, it's great for that. But other than that, without that vertical acuity, it's really a tough tool to use and help the client understand his project. This particular site, it's a 900-hectare site. There's 16 acres in a hectare, is that right? Something like that. So there's hundreds of acres. It's a huge site. And we think 30 or 40 of these now. Apparently, photovoltaic sites are common these days. Everybody wants to do it. This particular site is 8 kilometers south of Richmond. It's farm fields, forests, deeply inside valleys. I'm only going to show you the northern 400 because you lose everything because it's so huge. And we had 2 crews collecting, by the way, so it moved fast. I think it took us 10 days to do this. So we've processed this data out, and then we compare it in depth to this 15-layer model to see where there's a break. And in this particular case, we saw there's a break about 40. And we had 300 borings, and there's more about that later. This is where communication with your client is very important, and seeing the primary data your client has is even more important, because our client just told us top of rock. This is where top of rock is from all these 300 borings. Things you should note is that this works really well if there's a thick clay layer, obviously conductive, and heterogeneous soil, and this is important, can produce poor data. So you have to understand the geology. If you go from a limestone to a shale, you're going to have a totally different top of rock break. So the 40 ohms is not going to work. And like I said, different formations require different recalibration. So this was our answer. We looked at that and we go, there's absolutely no correlation whatsoever. But then we started looking at the numbers and we saw 0.6 is 2 feet. We had something like 30.6 meter borings. It's like 2-foot borings. These were test pits. Then we saw there were 0.9, there's 2.4, which is 8 feet. And there was lots of those. And I was like, how did they went up this whole 900-hectare site and they found all these 8-foot depths to top of rock. So we got the client to give us his data, and this was just the contracted price. They put it down 8 feet, got moved someplace else. So we had to go through each and every one of these and removed 200 records to get the real data. Oops, I wanted to show you this. So it's not perfect. This is not a perfect method. This is a helpful method. This helps our client focus on what is important in his site. This is a 900-hectare site, and he can't spend the rest of the time trying to figure out where the problem areas are. So this is a geologic map of the area. You can see I've got colored in blue here, possible sinkholes. This is probably not a sinkhole, but that one, probably that one's a sinkhole. But anyway, I colored in the ones where there was closure. We had LiDAR data. This doesn't show LiDAR data. We had LiDAR data that's superimposed on this so I could see these closed depressions. And we have the Drake's formation with the 2 members, Preacherville and Roland. Both are clean limestone. They both have known karst features. And then underneath them in the green is the Reba member of the ashlock. And that's important because we're going to look at this right here, this little square right here, and see what's going on there. And I didn't pick this area any different than any other, just we had a lot of data there, so wrong way. So what happened here? Why didn't we cover this area properly? Well, we can't do roads. We can't do this guy's property. He doesn't want us to touch it. You know, we have tree lines here. We have a creek bed here. And just a lot of issues that we couldn't approach with this method. So that is a drawback. But we were able to cover quite a bit of area for the client in a short enough period of time that he can use this data. And you can see in the top of rock, we see several deep areas. And of course, we focused in on these so we get better resolution. So I'll just show you one of the areas we focused in. It's that one up there. We had a bunch of borings there, so that gave us a lot of control. And if you remember, that REBA member was in the southwest corner, and you can see here we don't have the best control. This should be about 3.2. I think that's what should be 3.3 meters, and it's 1.8. So it's not perfect. But what you're seeing is the difference between something that is 2 meters and something that's deeper, and it shows that. But let's look at this one up to the north. Here we got good correlation. Actually, we got it a couple of them. We got good correlation up here and good correlation down there. But so that gives us the beginning of this project. Now the next step is focusing in on these areas with other tools. The more tools you use, the more information you're going to be able to provide your client. Oh, I showed the ash block there and the roll-in up there. So we ran shear wave seismic, and I think this was MASW, but it might be refraction. I'm not really sure what they did. But you can see here that that particular square shows this event very nicely. Can you measure it accurately and tell the client that it's such and so feet deep? You can get pretty close. Is it a void? I don't know. But it's definitely something different than the area around it, and it's something they need to pay attention to when they're doing their construction. And so the recommendation to the client is, put a boring there. So that's what we did. We went around to all these areas, looked at them closely with EI, and I don't know why this one was done with seismic. Whatever they did. There was some reason they did it, and I forgot to ask Alex why he did that. But so you see I put the logo there too with my dog. It's tertiary data. It helps the client understand what's going on. It's not the gospel, it's just tertiary data. But it does help the client. The frequency domain is great for giving you large areas quickly associated with the UTV, or you can carry it, but carrying is a lot slower. You need that multi-dipole tool so you can see and get some vertical acuity to what's going on. And it's fairly easy to process. Access is terrible, though. It's really hard to get this thing around. You saw how it sat on the front of that gantry platform. It's just very difficult to move around. It rocks, and it doesn't go through trees. You have to compare it to boring logs. And if you don't have them, you're in big trouble because you can't guess your way into this without knowing at least something out at that site. And any lithologic changes, you've got to revalue your formula on what you want to look at in terms of your resistivity value and the way we did it with this program. This is a Dutch program out of University of Delft. And are there any questions? Since I'm the moderator, I guess I can ask that.
Okay, so this talk here I'm doing is kind of a fun little experiment, to be honest with you. It's a opportunity that we had to, of course, help our client out here. It's in a site a little bit west of where Heidi was talking about, and so actually Heidi gave us some stratigraphy this morning that, if you're paying attention, it was the rocks we're going to be working in are in a slightly deeper section in the lower Cretaceous. So it's more in the central Edwards Plateau to the west, as you can see. So just kind of as a backdrop on what this project's all about, we were contacted by one of our clients at Arcadis. We're a consulting firm across the United States. But we were contacted by one of our industrial clients that mostly manufactures, but they do some mining. And in this particular case, they had a mine site where they're extracting gypsum, mostly for cement manufacturing as an additive to cement in the Austin and San Antonio markets. And they contacted us because they were having an issue with worker safety. It basically came down to having their equipment run across voids such as this void here, very near the surface, unexpectedly. And it was going on during preparation work for the mining. And I have a picture here of the mine setting itself. But of course, this is disconcerting to any equipment operator, and an even larger void could have led to injury or death. So this is a serious situation, of course. I want you to kind of take a mental snapshot of this picture. This is one of the larger karst features that we found at this site that had a lot of residual soil buildup in it. And a little bit of limestone caprock showing up here, but this is going to be one of the anomalies I'm going to show, so just take a snapshot. So the setting here, when I'm talking about extracting gypsum, it's a 6 to 11 meter thick gypsum seam. It pinches and swells. It's in the between the Segovia and the Fort Terret formations. It's the Kirchner evaporite bed that Heidi had pointed out. And the process that they use is to essentially scrape off the upper limestone caprock, and then they go in and drill and blast this gypsum, which is what you see in here, and put it in trucks and haul it off. They go through a crusher before they send it off. Topographically, this site is on the highest point all around, and so it's at the top of the hill, and groundwater is in excess of 175 feet here, so this is a high-end dry site. Topographically, here's the study area I'm mostly going to focus on. It's almost the highest point, and therefore all the rainwater that falls in this site is going to either run off or infiltrate through the rock. So a lot of vertical water movement. So here's kind of a cartoon of the going back here. This AA prime, kind of a cartoon of the current mine at that time, and then the 6 to 11 meter gypsum bed with the Segovia formation and limestone caprock, kind of a buff-colored limestone, and then the mixed limestone and dolomite in the Fort Terret member. And just kind of go through, I had some pretty good high wall pictures, so I thought I'd kind of step through sort of the process that we observed at the quarry in different stages of development in the karst formation process, starting with the bedded gypsum over here with probably a lot of these are blast-induced fractures here on the high wall, and then progressing into dissolution, which in a lot of cases occurs in sort of vertical tubes. So from top down, tends to develop in these almost pipe shape. You'd think that they drilled the holes are so perfect many times. But from a bird's eye view, it's more of a honeycomb pattern for the water to drain through. So that's how the precipitation is getting down into the deeper formations. Eventually, some of these dissolution tubes merge, and you end up getting small cavities, such as here. Here's another one where you can see the caprock sitting above the gypsum, which has got the vertical tubes in it. And when you carry this process out over here to its extreme, you end up with a cavity such as this one, where it's all collapsed. and then it can start raveling up to the surface. And at the extreme, here's a case where you can see there's gypsum over here and gypsum here, and it's completely gone in the middle. And this synclinal looking feature here is a thorough collapse of the overlying cap rock down into that completely missing section of gypsum. So this isn't a worker hazard at this point because there's nothing left. So this is the point at which it is a worker hazard. So this is primarily what we were contracted to try to analyze and find a way of locating for them in their working areas. Oops. Okay. One more. There you go. Just wanted to show you a couple exposures again of the cap rock. This is actually the medium that we're going to be collecting geophysics on top of, this variable thickness cap rock, the limestone. In some cases, it's sloping as the gypsum thins. But that's actually the surface that we're working on, not the gypsum itself. So we tested a couple different technologies. A little bit of this is kind of in keeping with what Peter had just been talking about, trying to use something that's cost-effective, that's qualitative and indicative, and not necessarily analyzed to the nth degree, but something that can be used cost-effectively to cover large areas. And that's this. We use a different frequency domain technology than Peter. And in my paper, I really go into details on how we evaluated this GEM2, this made by GeoFX. But the bottom line is that this particular technology uses, instead of multiple coils, it uses a single coil and varies the frequency it transmits rather than working with separate coils with different separations. A little different idea, and you can look in the literature and find out what people think about it, but we tested it here. This is the area that we were studying. This is the prepared surface, or pre-stripped surface where they've taken the veg off. So this is cleared of all the sagebrush and mesquite, and it's down to bare soil. And so at this point, they're wanting some kind of a study to go in here and say, before we start ripping this limestone out of here, what are we going to run into so that we can avoid it? And this is ERI. We've heard a lot about ERI in this convention, and then some MASW testing as well. So the study area, the red outline is about 5.5 hectares or 13.5 acres. And this study area in the red outline is where we did a bidirectional grid of GEM2 using multiple frequencies, which those different frequencies theoretically would give us different depths of penetration, so to speak. And if you analyze all those different components together using 1D inversion modeling software, you can estimate vertical models theoretically. In addition to the location of the GEM2 lines, they were nominally spaced about 5 feet apart. We had 3 test lines. 2 and 3 were resistivity only, and we did a segment of line 1 with seismic and then the full line with resistivity. And then all these symbols are the boring locations. Our client owned a drill rig, so it was a really nice situation where they basically said, go out and drill as much as you want to ground truth your work, which is, that's our dream, right? So, it's like, when I got up to 40-some borings, are you sure you want to don't you want to do some more? So, gosh, yeah, I'll take you up on that. So, and they even furnished on a second phase, they even furnished a video camera. So I'm just going to drop on one of the GEM2 maps. I think the one that we found to be most useful. This is using 80,000 hertz transmission frequency. We played around with lower frequencies to quote unquote see deeper, but I really felt like this one told us just as much as all the rest of the maps. And this is how we're going to read this. So we've got electrical conductivity that goes from basically non-detect or near zero, if you will, basically below the capacity of this instrument to even quantify. In fact, a lot of the values were zero or negative, which basically meant it's so resistive that it can't play with that. And then from there, we'd go up into the 30 to 40 millisiemens per meter conductivity range. For calibration, here's a stockpile of fresh soil that they had stripped, and you can see that the conductivity of that soil is in the upper 30s to 40 millisiemens per meter. So that gives you a rough idea of the conductivity of the soil itself. And then some of these areas out here, we know that it was scraped clean down to the limestone cap rock, and it was a good, hard, clean exposure to the limestone, and that's where we are typically getting 0 to 3 millisiemens per meter at best conductivity. So the conceptual model we had is that karst features, some kind of solution development going on underneath this cap rock, would tend to create some downward bowing of the cap rock and some fracturing, which would allow water to flow through, chicken or the egg here, but that would bring in fines into those concentration areas. And so we tended to see a lot of these little concentric anomalies in the Gem 2 that varied anywhere from, say, like 10 to 15 millisiemens per meter, all the way up to well over 25 here in this bigger oblong anomaly, and that's the one I had the picture of earlier with the brown soil that had fallen into the sinkhole. So the idea was to go out, and we definitely drilled a lot of these anomalies to quantify whether or not there was pure cap rock found, and then gypsum, or what the combination was, and just maybe to focus a little bit more on where voids were found. The ones with the blue dot are the ones where some degree of void was found. In some cases, the void thickness exceeded, put it in meters, like upwards of 2.5 to 3 meters in some cases. So it's a pretty significant drop in the drill rod. Although the problem with the drilling is, what's the nature of the void? Did we just happen to drill down through a couple of those honeycomb tubes, and otherwise it's competent rock, so there's not going to be an issue, or is it truly a cave? It's hard to say just with this technology. I will say, and before I go on, that the client was enamored with this product, and I was a little bit dubious that we could call this actionable by itself, but I will say he put a hard copy of this in the bulldozer, and the anecdotal feedback that I got is every place where we had color, they found some sort of a missing rock zone, whether it was something that was hazardous or just kind of an occurrence of a little void. They did anecdotally say that this was very useful to them. So you have to say, the operator appreciated the simplicity of it. So there's something to be said for that. So just to put you in context, so we're going to jump to line 1 here first. And this is all in the paper, so if you want to go back and look at all these in detail, I really encourage that. But I basically have keyed in the findings from each of the borings that we did along here, and all these lettered anomalies are discussed in the paper. But the honeycomb pattern is the occurrence of a void. So there's a small void here, pretty nice sized void here. So the conceptual model here is that the Gem 2 is picking up on, mostly it's going to be picking up on this. So this is low resistivity in the reds, high resistivity in the blue up to this wiggly pattern. So the Gem 2 is picking mostly up on this shallow soil accumulation. So what did that soil accumulation signal, right? Well, in this case over here, for example, in this anomaly D, there's a high resistivity zone that coincides with the low resistivity Gem 2 anomaly here, and the end of the cap rock coincides pretty nicely with the transition from low resistivity to high resistivity. Over here, actually I didn't point this out, but there's actually a little cave over here, cave opening, very small. I mean, it's rabbit-sized. And that cave links up with this especially high resistivity anomaly here. The entry at the surface. I'm speculating that that's the cave that little entry goes into. So the most resistive anomaly here, we didn't actually drill this. There was some practical reason why we couldn't, but it does look like it does link over to this void here. So what's left over in between these high resistivity zones are things like this red area here, this guy here, this one here. There was no void found, and you can see it was described as gypsum. So you start to get a sense that the gypsum has a low to moderate resistivity. I mean, it tends to be a material that has a lot of porosity, and there's a lot of soil in between some of these fractures and tubes that you see. So that's an electrically conductive material, surprisingly enough. The mineral gypsum, I'm sure, is resistive, but the whole environment is conductive. So what we have here is just kind of a series of basically nicer gypsum section with voids in between. One thing about the resistivity, and I've noticed this on everybody's resistivity, and certainly ours, is that the intent was to understand what was going on up here. And this is run-on, that's what I like to call it, the edge effects, where we didn't get enough resistivity field data out there to really model what's going on in this deeper section. And so typically you'll have a lot of these, what looks like a vertical column in the resistivity, and it's really uninformed data. I mean, we probably didn't get enough data to really say anything about this lower half of this section. And that example I showed yesterday with the cavity that they struck with the drilling is an example of why we collected resistivity data so much deeper, is because we want to get that density of data underneath, and we sacrifice some resolution to get the full encompassing of the feature. This is the only MASW test we did. Unfortunately, we ran out of time and patience with this with the client. But essentially, the voids are showing up in the MASW, not surprisingly, as a low velocity zone. Again, is it really a void, or is it a network of solution dot little tubes? Hard to say, but something is still carrying that shear wave, so it's not completely cavernous, or I wouldn't expect to really even have data we could interpret. So here's just another example. I'm not going to dwell on this. This is in the paper again, but once again, I'm just seeing the correspondence of good gypsum showing up in the lower resistivity, and then we have the occurrence of voids with the higher resistivity. So this pattern repeats itself. This is a particularly nasty looking anomaly here. In the Gem 2, again, that was like well over 25 millisiemens per meter. You can see this is extremely low resistivity material, and you can see why with this brown soil, has a lot of moisture content. No surprise there, but there is a very high resistivity anomaly underneath it. I don't know that it is real down to this below the floor, but it is possible that this could be an older karst feature in the underlying limestone. And this may be an unusual occurrence for this site. It's not really necessarily a gypsum feature, but maybe a limestone feature that's projected up through. So how am I doing on time? One minute? Okay. I had some videos, but maybe we'll look at it on a break. But essentially, I guess the takeaway I wanted to give you on this conclusion, and by the way, here's the John Henry rig they used to do all this drilling for us. But again, kind of like what Peter was saying, it's like, our clients want us to leverage on the dollars they spend on these surveys. And if we find something, even if it's sort of an indirect indicator of a problem area, this Gem 2 did an outstanding job of at least focusing our thoughts. And when we compare that to the resistivity work, it said, hey, the Gem 2 basically said, hey, there's something down here. It didn't say what it was, and if the client wants to know what it was, then they can drill it, or we can go out and do resistivity, right? I mean, there's a variety of things you can do. But there are limitations to a thing like this Gem 2. I mean, it does a horrible job of quantifying resistivity. I mean, basically those instruments only quantify conductivity. So essentially, when you get into the resistive realm, they basically go off scale and don't give you any information. So they're not good at detecting error. So that's just the way the frequency domain EM works. So understanding that limitation, you're looking for the conductive element in a larger space. If you understand that and know how to deal with that data, I think it works well. And again, I mean, I've got borehole videos I could show you if I had another half hour, but essentially the borehole videos, what they show you is, in fact, some of these places that look like high resistivity, moderate resistivity, were in fact a bunch of tubes that the driller said was a void, and ended up being a bunch of pieces of gypsum standing up in this hole. So, again, they're high resistivity. If it's really high, it might be a big void, but if it's moderate, it might just be, a high porosity. So that's what I got. I guess I'm out of time. So
yeah, let's hold off on questions because he ran out of time and want to keep on. You can talk to Greg afterwards.
Yep.
Lewis. Lewis. Our next speaker is Lewis. You know him from Nickery, so he needs no introduction.
Excuse me, Lewis, would you mind taking your lanyard off?
Taking my lanyard off?
It rubs against the mic, causes static.
Oh, okay.
Thank you.
Okay, well, I'm not sure if I need no introduction at all. My name's Lewis Land. I'm with the National Cave and Karst Research Institute. And I'm going to be talking about just finding out what the upper limits of electrical resistivity profiling are for a project that we worked on at Carlsbad Caverns National Park in New Mexico. And by we, I mean me and my co-author, Michael Jones, who I assume is in the audience out there somewhere. Let's see, and advance this by using that up arrow maybe? The down arrow. Oh, okay, that's kind of counterintuitive. All right, so this project started out when we at the Cave and Karst Institute got a call from people at the National Park Service at Carlsbad Caverns National Park, which is just about 30 miles down the road from our office in Carlsbad, about an excavation that they had planned near their park headquarters. And this excavation is going to cut into karstic dolomite bedrock, and the park staff were concerned about encountering void space along that course of that excavation, that is, small caves. And so they knew that we had electrical resistivity equipment we often use for locating caves and potential sinkholes. And they contacted us to do a resistivity survey in the vicinity of that excavation to see if there were any little caves in the area that they should avoid. So this is a pretty straightforward concept so far. Now, just to show you where we're at, Carlsbad Caverns National Park is located on the southeast-facing escarpment of the Guadalupe Mountains in southeastern New Mexico. And the visitor center and the park headquarters are constructed on dolomite outcrops of the Permian Tanzil Formation. The Tanzil Formation is the host rock for some of the upper passages of Carlsbad Cavern, as well as quite a few other caves in the park. Now, I should point out, a lot of people don't know this, but there are actually quite a few caves in Carlsbad Caverns National Park. I don't know the exact number, but there are a lot. A lot of them are only accessible with a permit, or they're ranger-guided caves. But there's Carlsbad Cavern itself, which is the third longest cave in New Mexico. It's famous for its big room, all of its incredible cave formations, the largest cave chamber in North America by volume, all of those other superlatives. It is world class. It is a World Heritage Center for good reason. But there's also other really cool caves in the park, like Spider Cave, which is famous for its exotic cave formations like these helictites. and Lechuguilla Cave, the second deepest cave in the continental United States. So Park Service personnel at Carlsbad Caverns are understandably protective of these world-class cave resources. And that's why they contracted us for this project, to protect any potential cave resources that they might encounter during this excavation. Well, okay. So they knew we've been using electrical resistivity methods to locate cave passages, among other things, for more than 10 years. And it's a very reliable technique. There are good reasons why you've seen so many resistivity surveys during this presentation. And there are good reasons why some of these other methods that people might have used in conjunction with them don't even get talked about. But, you know, I'm just to refresh people's memories, or for people that aren't familiar with the technique, you know, the basic principle involves generating a direct current between two metal electrodes that are driven into the ground and measuring the ground voltage between two potential electrodes in between them. And if you know the current flow and the voltage drop, then you can identify and map electrical resistivity in the subsurface using specialized software. So in the olden days, you know, there are several different electrode configurations that you can use when you're doing resistivity surveys, and one of the simplest that you learn when you're an undergraduate is the winner array, which consists of these 4 evenly spaced electrodes in a straight line here, and the current electrodes that inject the current are at the ends of the array, and the potential electrodes are in the middle. But this is the winner array, and so you inject current into the ground, you take a measurement, and then you move all 4 electrodes farther apart so that you can see deeper into the subsurface, take another measurement, then move them apart again. This is the technique that I myself used when I was a humble undergraduate in field camp when we had a week of geophysics. This is really labor intensive, and in the bad old days of the mid-20th century, this is how we did ER. Fortunately, those days are behind us. So modern electrical resistivity surveys use an array of multiple electrodes that are all connected with electrical cable, and over the course of the survey, you can activate pairs of electrodes using an electromechanical switch box and a resistivity meter. So the switch box and the resistivity meter will say, okay, this pair of electrodes is the current electrodes, these are the potential electrodes, and just go on down the line. It's all fully automated. It's a lot easier. It's still pretty labor intensive, but much easier than in those olden days. And the specific array configuration that you use is dictated, and for our equipment at any rate, by a command file that you create with on your laptop using this software, and it's uploaded to the resistivity meter. And this is going to be kind of important. Now, because air has near infinite electrical resistivity, it's easy to detect air-filled cavities because they'll strongly affect the results of your survey. And they'll display as zones of much higher resistivity, basically off scale. If you're dealing with, say, a flooded cave, which we have dealt with in the past, then that will display usually as zones of lower resistivity. And we have found that our exploration depth of our equipment is usually about 1/5 of the length of the array. Your exploration depth is basically dictated by your electrode spacing, but in the real world, that means the length of your array will determine how deep you can see. Okay, so this is just what our equipment looks like. We use equipment from Advanced Geophysics International, a company based in Austin, Texas. They manufacture a resistivity meter that they call the Super Sting in this colorful yellow and black box here. And there's the switch box that we use right there. Here's our array of electrodes all connected up with electrical cable. And the whole system is powered by these deep cycle lead-acid marine batteries, which are really freaking heavy. I used to go to CrossFit workouts, and there was a workout that we would do called the farmer's carry, where you pick up these weights and just walk 100 meters and then back. Same thing when you're dealing with these lead-acid batteries. Okay, well, and this is just a close-up of those electrodes that we use. Our electrodes in this case are 45 centimeter stainless steel cable, and they're connected to the cable with that spring there. And some of the results that we've gotten in the past look like this. This is, in this case, that's a big void space on the subsurface filled with brine, and it shows up as a big low resistivity zone. And the maximum exploration depth that we have been able to achieve with our system has been about 230 meters using a 112 electrode array, a 112 electrode pole dipole array at 6 meter electrode spacing. Now, it's a really interesting experience using a long array like that because something always goes wrong at the beginning of the survey. like the cable has been knocked off of an electrode, and it'll be way down there at electrode number 99. So I'll have to ask my assistants to go tramping thousands of feet down the length of the array to see what the problem is. Cell phones and walkie-talkies are really helpful under those circumstances. So this is another example of a cave that we surveyed over. This is one that we surveyed in West Texas. It was, again, a cave flooded with brackish water. And in this case, we had that cave had been surveyed by cave divers who, in my opinion, are kind of mentally ill. But they did a really great job of surveying this cave. And the map, of course, was projected to the surface. So I knew exactly where the cave passage was. And when we first started doing this work, I intentionally ran a survey line directly over the cave to see what it would look like. And it looks like pretty much what you would expect. This is where the cave was located, and it's about 11 meters below ground level. About 20 meters below ground level, and it looks like a big low resistivity pod. And we knew the cave was there. This here is probably another cave, another conduit that just had not been surveyed. So anyway, so you can see this is a really cool and effective method. Under the right circumstances, works great. Now, the proposed excavation of interest at Carlsbad Caverns National Park was a trench for a utility line that they wanted to dig. That would be 55 centimeters, 22 inches deep. Okay? Now, those of you that are familiar with resistivity methods are probably thinking the same thing that I did when I heard this. So when George Veni came to me and told me about this project, I thought, that's just stupid. I pointed out to him what George already knew, that there are a variety of different geophysical methods that are a lot more suitable for an investigation this shallow. I mean, GPR immediately comes to mind. I've heard stories about engineers using ground-penetrating radar to locate rebar in concrete parking lots. Works great for stuff like that. Why not use that? Well, they didn't want to do that. The Park Service knows us. They know that we have resistivity equipment. We're right up the road. They really wanted to work with us. And, you know, if they hired and we didn't have GPR, if they hired a geophysical consulting company, it would probably cost a whole lot more. As it is, the budget for this was really low. They were going to pay us with the Park Service credit card. I thought this might be kind of an interesting mental exercise, if nothing else. I did not think it would work very well, but I thought, well, let's see what we can do. So I did some field trials that used a 28 electrode dipole-dipole array, the shortest possible array we have with our equipment, and moved the electrodes closer together to just a 1/2 meter electrode spacing. And I also had a consultation with AGI technical support in Austin. Those guys are great. You buy equipment from AGI, they're your friends for life. They provided me with a modified command file that was designed for a shallower exploration depth that would instruct the SuperSting resistivity meter to collect the highest resolution readings down to just 5 meters, and then just remove all the deeper readings. And the results of the initial survey were bad. They were really bad. They were appallingly bad, just full of artifacts. And it just didn't work at all. I think that the Earth Imager software that we use removed something like 20% of our data points as outliers. And it appeared that at such a close electrode spacing, the electrodes themselves become sources of interference with each other. So really bad, sucky bad results. So anyway, I went out into this big field next to our parking lot. And I should explain, by the way, that the trial area where I was doing these field trials is on the floodplain of the Pecos River. So you're basically dealing with alluvial sediments. So these subsequent trials in this open field, I used that modified command file at 1 meter electrode spacing, and I used what's called that suppressed noisy data option in Earth Imager, a useful tool under some circumstances. So this array configuration worked out pretty well. We got an exploration depth of 4.9 meters, shallower than anything I'd ever achieved before. Before this, the shallowest I'd gotten was like 10 or 11 meters. And most of the time, you know, I want to go deep. I used to work in the petroleum industry. I want to see really deep, you know, like industry level deep, 15,000 feet. This is all near surface stuff. So deep for us now is like about 230 meters, like I said. So 5 meters, I thought, that's pretty good. And it shows, as you can see, it's got a pretty boring profile, really, not surprising. almost entirely uniformly conductive material, less than 20 ohm meters. And this all probably represents all these fine-grained silts and clays that are alluvial deposits of the Pecos River floodplain. And you'll see these two little pods of high resistivity here, and I think those are probably air-filled animal burrows. I suggest this because there were animal burrows all over the place in that field. And so that's not terribly surprising. Their size has been enlarged, I think, because of the iterative process of the Earth Imager software. But this was encouraging. This suggests that we could actually see very shallow voids, maybe less than a meter deep. So now we have a system that we think is going to work. And so my co-author, Michael, and I, so we go the following week, drive out to the park and set up our array. So let's see. Now, that's going backwards, sorry. Oh, I should point out, by the way, this is a resistivity survey I conducted in that field in exactly the same location the previous year. But this, in this case, I was using it was a more conventional survey, using an electrode spacing of 1 meter, and you can see pretty much the same thing. It's just that see this shallow conductive layer right here? That's what, oops, I'm going the wrong way again. There we go. That's what we're seeing there, all above about 5 meters. You're seeing the same thing right here. You're also seeing a lot of other interesting stuff too. That discontinuous layer of higher resistivity you see about below 3 meters, that's probably air-filled porosity in coarse-grained lenses of sand and gravel. And those are probably old channel sand deposits in the unsaturated zone. This is really common. I see this all the time. But it's encouraging. That's the kind of thing that you would expect to see. So the system works. All right, now the study area out here, this is the study area. This is the road that goes up Walnut Canyon up to the top of the escarpment on the southeast flank of the Guadalupe Mountains. Here's the visitor center here. Here's the park headquarters, and here's our little resistivity survey line right here. That's where they were going to dig that trench. Now, so we did 2 resistivity surveys parallel to that proposed utility line using a 112 electrode dipole-dipole array at 1 meter spacing and using that modified command file. And the second survey we did used the same array, but just for comparison, I just used a standard dipole-dipole command file, so same kind of thing I would ordinarily use. And you can tell this survey was conducted in 2020, and you can tell that because even though I'm out there, I'm wearing a mask. Those days, fortunately, are behind us. And this also gives you an idea of what the substrate is for the survey. We are looking at a few centimeters of just old, compacted roadbed material on top of dolomite bedrock, which made the installation of the electrodes extremely challenging. Fortunately, my co-author, Michael, is a former high school football player, so I relied on his great physical strength to drive those electrodes into the ground under my supervision. And but also because of this substrate, we got a really high contact resistance of like around 200,000 ohm meters, which is about 200,000 ohms, which is about 100 times greater than AGI recommends. And so we used about 20 gallons of salt water to water the ground around the electrodes and improve the contact resistance and got it down to about 25,000 ohm meters, which is still freaking high. But gave us a really noisy data set with an RMS error that was like over 37% on some of our trials. So it was a long 2 days out there. So because of that really high noise level, I revised those Earth Imager inversion settings again, and I used that suppress noisy data option. And what that does is it employs something called the L2 norm, weighted data misfit approach, to determine your error factor rather than root mean square. And so our target, if you're using RMS to evaluate the quality of your data, usually you want to get under something like 10%, lower than that preferably. With L2, your target L2 norm value is less than 1. And again, you can kind of see what the substrate looks like here. This was really difficult. And I should say that the park, because it's a national park, they didn't want us to use a hammer drill to drill holes into the ground and install our electrodes, which is what I usually would have done. So we just had to rely on brute force and a sledgehammer. So this turned out to be a much harder job than I thought it was going to be. Let's see. Well, Having made those changes, though, we actually got an L2 value of 0.73 after only 3 iterations of that inverse model, and we got a maximum exploration depth of just about 5 meters. Here's the elevation on the side right here, 1342 to 1348. So I was really pleased with that. And here's what the results are. The maximum resistivity of this survey is a little bit less than 16,000 ohm meters. Now, if there were, in fact, caves in the area, I would expect that basically if it's an air-filled cave, your readings are going to go, it shows up as around 100,000 ohm meters in this Earth Imager software, which essentially means that it's going off scale. Well, so 16,000 ohm meters is high, but it's not super high. That's the kind of what you might expect from dolomite bedrock above the water table. And so that would suggest to me that there probably are not any air-filled voids present in the survey area. So it's just this near continuous, God damn it, just a minute, bear with me for a minute. So you see this near continuous layer of high resistivity that extends all the way across the profile, almost certainly indicates the presence of highly resistive dolomite bedrock at or very near the surface beneath the survey line. And we didn't need any boreholes or anything to provide ground truth because we were walking around on it. I have never encountered a more difficult field area when it comes to installing electrodes. After we were done, some of our electrodes were very slightly bent, and I learned that when you take an electrode that's just very slightly bent and wail away at it with a sledgehammer to get it into the ground, when it comes to getting it out, you've basically turned it into a corkscrew. And so late in the day, Michael and I ended up using a hammer drill to excavate around some of those electrodes to get them out. We never told the Park Service people about that, so don't mention that. Oh, there's Park Service people in here. Okay, so this worked. Now these results, in my opinion, are kind of boring, but anyway, just for comparison purposes, the second survey we just used a standard dipole command file, and we got an exploration depth of about 16 meters. But it is entirely consistent with the results of the shallower survey. So here's that layer of high resistivity right near the surface, and here's what this more conventional survey does. And you can see we're getting pretty much the same thing. So I think that's very encouraging too. And you can also see this conductive zone that you see at about 5 meters depth. That's probably a perched aquifer in the Tanzil dolomite where it overlies less permeable sandstones of the Upper Yates sandstone. And you can actually see that perched aquifer. I'll show you a picture of it in just a minute. It's just about 800 meters northeast of the survey area, one of these overlooks in Walnut Canyon. And here's the two of them side by side. So you can see the shallow survey, boring results, frankly. And incidentally, speaking of boring results, most of us as geoscientists, we want to see really cool stuff in the subsurface. It's kind of interesting to see caves and things like that. I've learned that a lot of our clients would prefer not to have exciting results. They would actually like it a lot if our results were boring. I see engineers in the audience nodding in agreement. So anyway, boring results, but the system worked, and this was it was an interesting thought experiment. I think because 5 meters, I never would have thought it possible to get an exploration depth that shallow with resistivity methods. And and this is that picture that I was telling you about. Now, since I live in Albuquerque now, not in Carlsbad, I couldn't just drive right down the road and take a picture of the road cut. So I just used the Street View and Google Earth to get a picture of the road cut and see. Which is, technology these days is just amazing. So you can see this is the Tanzil dolomite right here, and this is the Upper Yates sandstone right here, and you can actually kind of see some staining right here where water is seeping out of this, what is essentially a bedding plane spring right here. And that's what I think those conductive zones at greater depth on the conventional array were probably, that was probably a perched aquifer in the Tanzil. So our conclusions, again, are not, this report was basically about methods because I'd never used methods like this before, and it was a lot more work than I thought. The results were perhaps not that great, but were not that interesting, but they were happy to see non-interesting results. So we've demonstrated that resistivity surveys, when they are configured for such a shallow depth of investigation, can still provide really pretty useful information about near-surface conditions. So I would just like to thank my co-author, Michael Jones, who's now working on his master's degree at the University of Arkansas, for all of his really hard work in helping me to do this survey. And so at this point, I'll take any questions you might have, except questions about RMS or L2 norm, because that's a little bit out of my field. So I'll defer you to my co-author to answer those questions. Okay. Oh, it's 10:45. I'm right on time. Okay.
Lewis, did they dig the trench?
Yes, they did dig the trench, and they did not find any microcaves. Yes. Probably not. I don't really know the details of the excavation. That was sort of, I went out there and did the survey, and then that was, and that was that. But from what I understand, they dug the trench somehow, and they didn't find anything of concern.
I saw in your picture this structure, metal structure. What's that?
Oh, it's some kind of an antenna. I'm not really sure. Surface metal structures like that usually are not that much of a problem with resistivity surveys. Overhead cable, I don't think is really that much of an issue. It's buried metal structures that create all the interference. And we confirmed that there were not any buried utility lines or anything like that in the survey area. Oh, somebody else has a question over there. Or you? Oh, yes.
Hey Lewis, a very good presentation. Actually shows the kind of the extremes that you can take this to. And the command codes that you got from AGI, was it optimized through any kind of least squared method or anything like that that allows it? Because Wilkinson and Loki developed a lot of optimization coding for it. And that kind of allows it to jump around and drop that parasitic charge a lot.
Yeah, I'm afraid I don't actually know. It's when I get questions like that, sometimes I tell people that I'm not really a geophysicist. All three of my degrees are in geology, and but I will say. But so it's just the modified command file was provided to me by Jason Greenwood, who's the software tech support guy at AGI. Right. And he was extremely helpful. I had multiple email exchanges with him, but I'm afraid I can't answer your question.
Yeah, very interesting. It actually shows the extremes that you would get to. Thank you.
I was surprised. And I was also surprised when I did what, as a geologist, I thought was the most obvious thing, was just to move my electrodes closer together, and that'll do the trick. It had exactly the opposite effect.
Yeah, I'm just a dumb engineer, so I have a little question to ask. I mean, in both of those profiles, you don't say that they're both using the same electrode spacing. Yeah. So you're just using a different command file.
That's
to
right.
Run that. Now, is that command file just processing the data differently?
Yes.
Or is it changing the voltage on the probes differently?
Oh, changing the voltage? No, I don't think so. It's just it's processing the data differently. It's just telling the supersting to just ignore everything below 5 meters, essentially, and just use the highest resolution data that's available in the uppermost 5 meters.
All right, thank you.
Good morning. We're in a Karst Clips session number 2.
Oh, do we have the clicker? Thanks, Issam.
As a reminder, these are 5-minute lightning talks. There's no Q&A associated with them. These are the talks that we're going to be having up here, and we also have one additional short talk at the end by Dan Doctor right before we have our hour-and-a-half lunch break. So we'll start off with 2 by Michael Jones.
Okay. Thank you, Ira. Oh, sorry. Okay. So okay, let's go back. All right. So as you may know, CO2 is the primary control on dissolution rates in carbonate terrain. But what I'm interested in working on for my master's thesis is understanding what controls CO2 variability at a given site. So at the University of Arkansas, we've been building oxygen and CO2 sensors to deploy at different depths in the soil zone and the vadose or epikarst and in the phreatic zone. So we've been deploying these in wells and shallow wells in the soil, and then there's a groundwater well on site at the Savoy Experimental Watershed, which is owned by the university. The reason why we're monitoring oxygen with CO2 is because there's the apparent respiratory quotient theoretical line that we can compare our data to. So if respiration is the dominant control on CO2 production, there should be a one-to-one relationship between oxygen and CO2. And if it falls below this line, that might be carbonate weathering or dissolution. So we can look at CO2 variability, seasonal variability, storm scale, and diurnal. So this is just a snip of my preliminary data so far, where we have 4 CO2 sites, and we can compare to hydroclimate data, and you can see a general trend of CO2 lowering during the colder months or the non-growing season, but the CO2 does behave similarly to like a hydrograph. So after large rain events, we do see a peak in kind of a recession curve of the CO2. What I found really interesting was during cold fronts or freeze events, maybe the pressure dropped, and that caused the CO2 to lower dramatically. And I've been taking just spot measurements of discharge, where we've had a lot more rain in the last 2 months, which has driven the CO2 back up. And looking at my CO2 and oxygen data in the shallow soil zone, I saw pretty interesting results, which I didn't hypothesize that during the non-growing season that we'd be close to the ARQ line, but we were closer than previously thought. So as you're closer to this line, that would mean soil respiration is the dominant control. And we can also plot ARQ in a time series. This is the orange line is ARQ. So that's where, if soil respiration was the dominant control, the red line, the CO2, would match with that ARQ line. So I mentioned that we've had a lot of rain events in the last 2 months, and we've seen that when the soil the pore spaces are filled and the soil's very moist, we see that the CO2 actually is over or above the theoretical ARQ line. And plotting the data together, we can see these storm scale events, and I put pressure in black, where during these fronts we see a dramatic drop in CO2 levels, but we can also look at ARQ. So it seems like during those rain events, we actually have a drop in ARQ. So the main focus of this study is to see if soil respiration is the dominant factor in seasonal variability. When things warm up during the spring, we have a lot more rain events, but the biology is really ramping up, and that's when we see typically our highest CO2 levels. I'll probably just go on to the next talk.
Yes, thank you. Just a minute, let's hold on. I want to, can I have Scott Dyer come up to be on deck here? Okay, gotcha. Thanks. Yeah, go on ahead,
Right.
Mike.
And if you're interested in the work I'm doing, I also have the schematics and the code for the equipment I use for the CO2 O2 system, and it's a very inexpensive kit that we build, less than $400 to have everything, including a solar panel to charge your batteries. So I was going to share some of the work that the Carbonate Critical Zone Research Coordination Network's been working on over the last year to share data amongst each other. So we've been using the Python package ohm by Matt Covington to automatically retrieve data from the INWIS database. And we use the US Karst map to filter our sites to carbonate areas or siliciclastic areas near carbonate areas. And then we use ArcGIS to create a geodatabase that we can easily zip up and share amongst each other on HydroShare. And then the idea is once it's uploaded, other researchers could do a deeper dive into the data. So what we're mainly interested in is this gradient between carbonate terrain and silicate terrain, which John Martin talked about yesterday during the keynote. So last summer we started this project doing automatic data retrieval of karst springs or carbonate springs in the U.S. And we found that it was a really useful tool that we could share with other researchers where within a short amount of time they can download a tremendous amount of data. And with that we can share it with other colleagues. And Laura Torn at Temple University had a student create another Python package that basically took the GIS or the geodatabase and looked for trends in nitrate. So they found some interesting springs with kind of a trend of nitrate increasing over time. And more recently, this spring, Ellen Herman at Bucknell University is utilizing her students in her cave and karst class to do a similar thing around the karst in Pennsylvania. And the idea is when we are able to zip up these databases and share amongst each other, then depending on what you're really interested in, you can do a deeper dive. And then this spring we're hosting the Carbonate Critical Zone field workshop, but a part of that, prior to that, we have a training workshop where undergraduate students will train them to do some of these types of methods where they'll go out in the field, record data, but get an introduction to Python programming and to be able to create plots with their data. And the idea is to all meet together and create new ideas of what kind of publications or data that we're all interested in. Right now, we've looked at springs, but we hope to look at streams and groundwater, water quality data to help kind of answer some of these questions of why carbonate critical zone is so much different than the siliciclastic critical zone. That's it.
Thank you very much, Michael. Scott Dyer is up next, and Brian Cohen is on deck.
Real quick, to make the flow go a little more smooth, if you guys could enter and exit on this side, I will clip you. And please try to remember to leave the clicker either on the podium or on the table. So you clip this.
Where's the clips?
On the back.
Got it. All right, good morning, everybody. Got a lot to say in a short period of time, so I'm going to get to it. Sorry for the noise. The view you're looking at is Porter Hole Sink in Lake Jackson's basin, north of Tallahassee, Florida, which is the capital, in case you're not familiar with it. The view here is to the north. The area of the coalesced sinkhole basin is about 16 kilometers. The first recorded in modern history period of drawdown was in 1829 to a newspaper article. Since then, it's drawn down, I believe, 12 times now, including this view of the drawdown in June of 2021. I'm going to walk you through the study area. Tallahassee, here, capital, north, Porter Sink. As you will notice, there's the, woo-hoo-hoo. As you'll notice, where's the red? There's an escarpment here, Cody Scarp. And the northern area is the Tallahassee Hills province. Below the escarpment is the Woodville Karst Plain. Next feature I'd like to point out is the potentiometric surface. That is from a date of May 22. I'd like to point out that in the Porter Hole area, it's about 10 meters. As you proceed south from Porter Hole into the Woodville Karst Plain, a couple points of interest. To the east, Wassissa is the spring-fed river as well. Darn it, I'm burning my time up here. As well as St. Mark's River rise in this area. We've got Wakulla Springs, one of our main targets, and you'll see the blue mapped extensive conduits that have recently been expanded, one of the leading lengths in the U.S. What am I missing here? Oh, the most important thing. This entire study area is underlain by the upper Ford and Aquifer. As you can see by the classification of the shading above the Cody escarpment, that is confined, semi-confined. So the dye trace is transitioning from confined, semi-confined into a completely unconfined in the Woodville Karst Plain area. The impetus for this dye trace was the drawdown in June of 21. It had been previously traced in 2018 when it was not a drawdown circumstance. There was some want, need, desire to maybe confirm, duplicate that trace, which did connect Porter Hole Sink with Wakulla Springs. We saw this as an opportunity. Collaborators, Florida DEP, Northwest Florida Water Management, gave FGS the go forth and trace. So we did. Our first attempt was to, in a nutshell, kind of bracket to the west with the Ochlockonee River, to the east with Wassissa, step in, back to St. Mark's River rise, main target here, Wakulla Springs. We were trying to work within the potentiometric surface, condense flow, primary zones near the trough. We use groundwater monitoring wells, conduit monitoring wells, and in the groundwater monitoring wells, we were trying to get like a 3D flow path if we could. So Northwest Florida Water Management District provided us geotechnical logs that would allow us to kind of position and place our charcoal packs at preferential flow zones. Charcoal packs were used extensively. The only location we actually used is at Wakulla Springs, the ISCO sampler, so that we could actually produce a breakthrough curve if we indeed got a hit. So other than that, charcoal scrubs. We injected in August of 21. February 9th this year, we see sampling. The disappointment in it all, maybe 1,174 samples, no detects yet. So it begs the question, why no detects? Well, obviously, we did not sample in the flow path of the dye. Dilution, possibly. The distance from Porter to Wakulla Springs is 32 kilometers. It's likely that it got diluted. More likely, the impact of this consumptive use well fill for the city of Tallahassee. As you can see, there's 197 wells, 214 million gallons per day, averaging 114. The stage at the time of our trace was a lower potentiometric surface in the upper Ford, and so we feel that maybe our dye went lower and therefore was impacted by these 197 wells at varying lengths. So basically, the wells probably helped dilute, divert, or even extract our dye. Thank you for your attention. This final slide is a look at Porter Hole Sink to the south. You can see the exposed oven there to the right of the word geoscience. Thank you.
Thank you very much, Scott. Brian is up, and on deck is Issam Bou Jaoude.
All right, thank you. My name is Brian Cowan. I work with Stantec, and we recently started a project for the Texas Department of Transportation. And the project is within the range of an endangered salamander. This is the Jollyville Plateau salamander. It's got a face that only a mother could love. The project's about 3 miles long, and it's located in the northern Edwards Aquifer. The salamander itself lives only underwater, so it lives in the aquifer, cave springs, spring runs. And there were multiple potential habitat sites that we identified. All of these triangles within the project area. I'm going to focus on a detention pond up on the northern end of the project. We use multiple methods to try to detect their habitat or to detect them directly. Thermal imaging, gauging, geochemistry, and eDNA. And you can see that the project area here in red is right in the middle of a lot of critical habitat units mapped by Fish and Wildlife Service. So unfortunately the pond is underneath the highway. So the pond is, this is the outline of the pond. We have an inlet to the north, an outlet to the south. We placed a V-notch weir in the inlet that you can see here on the right. And that seam that you can see just behind the weir has groundwater flow or suspected groundwater flow emanating from it perennially. This is our downstream weir, same setup as upstream. And this is a view of the pond with our thermal imaging camera here at the bottom. So on to the data. We have our discharge, which this is a little snippet of what we've looked at so far. In blue, you can see our upstream discharge. This is what's coming into the pond. And then in orange, downstream. And you'll, of course, notice that we have more water going out than coming in. So that's telling us that we probably have additional sources of water entering the pond other than what we could see in that upstream end. We also looked at the geochemistry of the Warrior Pond that I'm talking about, and also multiple other springs located within the project area. We also looked at a wastewater treatment plant and some other local sources such as potable water and groundwater. Really, the geochemistry didn't tell us much other than that the wastewater is likely not the source. Everything else plotted pretty close together. Here's a picture of our thermal imaging data. This was taken on a cold day, so this is our normal image, and I'm sorry it's not showing up well. This is upstream, and then we have downstream. The water's emanating from right here in the seam, and then the pond is down this way. And you can see that on this cold day, the upstream surface runoff was distinctly cooler than our downstream outflow here. And the water temperature was roughly 70 degrees coming out of this seam, which is pretty much in line with what we see with the groundwater in this area. All right, on to the cool part. So we looked at eDNA. That allows us to take a water sample and look for the DNA of the target species, in this case, the endangered salamander. And we can do that by filtering the water through special filters, and then the lab will actually look for the DNA and amplify that DNA and tell us what's in the water. And we get that DNA through skin cells sloughing off, through waste, reproductive cells, anything of that nature. And it's pretty good at detecting species that are hard to survey for. It can take dozens of surveys to actually confirm presence of these salamanders. So this is us checking out our site here. We did 2 eDNA sampling events so far. We have one more planned for next week. There were no eDNA detections within the study site, so within the roadway project, but we did get a positive eDNA detection at a control site. The city of Austin has several springs under their management. One of the springs has one of the highest densities of these salamanders in it. And in fact, when we were out there taking the sample, we saw a salamander scurrying off as we were taking the sample. So we were able to validate that our eDNA methods do in fact work. So that really allows us to give TxDOT some good information in their planning of this project and also in their consultation with U.S. Fish and Wildlife so that they can get the proper permits and proceed with some good solid knowledge. That is it. I would like to thank TxDOT, of course. I would like to thank Austin here for all the muscle and hard work that he put into installing those weirs, and of course the city of Austin. Thank you.
Thanks very much, Brian. So Issam is up. He has 2 clips back to back. And then Luke Anderson is on deck.
So I'm going to try to present in 5 slides, 5 minutes, why a country is rich in caves. Let's see how it goes. All right. Okay, Lebanon is located on the eastern coast of the Mediterranean Sea between Syria, Jordan, and Turkey. It is 20 times less than Florida in size. And it has more than 700 documented caves. I mean by caves that the entrance is less than 2 meters, like the cave is 2 meters more than the entrance itself. So we're not talking about sinkholes or dough lines, which are more than 50,000 in Lebanon. So Lebanon, again, is on the eastern coast of the Mediterranean Sea. There are 2 mountain chains. So the western mountain chain with a maximum elevation of 3,018 meters, and the eastern mountain chain. And the length here is only 220 kilometers, and the width is 65 meters. The highest peak is around 35 kilometers from the coast. There is a small coastline and coastal plain, and an inland valley. This is how it looks. We have the highest peak here, 3,018 meters, around 30 kilometers from the coast. The Bexar Valley, which is a valley here in the middle, and then anti-Lebanon, and then Syria goes to this side. It is the only country in the Middle East which has no desert, and there's a lot of precipitation, as you will see. So the highest precipitation ranges between 200 and 1,500 along the western coast, and it actually blocks all the humidity that is coming from the Mediterranean, and that's why you have more desert in Syria in this area. And the total amount of precipitation is around 2 meters if we distribute it along the country itself. And then in terms of karst exposure, it's around 65% exposed, but if we look at the covered karst, it's more than 95%. The land surface of Lebanon is 95% karst. And this is how it looks in terms of karst. There's the green, which is the Cretaceous. The blue is the Jurassic, and the Eocene is in orange, and the Miocene is in blue. And they're all karst, with more than 80% of the water sources coming from karst. In terms of structure, Lebanon is located at the Dead Sea Transform Fault. You heard about the earthquake in Syria and Turkey. They are further, like a few kilometers north of this, and it's at a restraining band. And when the restraining band is there, it creates a lot of compression, same as the San Andreas Fault that we have in the US, and it caused all this uplift and mountains here. And again, the Jurassic, we have the coastal flexure, and then the Jurassic here in blue, again, and then the Cretaceous in green, the Eocene in orange, and the Miocene in yellow. So anticline, syncline, and coastal flexure. In terms of karstification and history, after the Jurassic was deposited, there was a major uplift, and the land was exposed. So karstification started in the Jurassic, and then it was followed by volcanism. Volcanism, which also created karstification. And you can easily find the unconformity and the karstification at this stage. And then all this was deposited with sand and delta-like structures, and then the Cretaceous were deposited again with volcanics after them, and then karstification also developed in the Cretaceous and in the Jurassic. Again, then the major uplift occurred in the Oligocene, and this is where the major structural features developed, and major karstification also occurred at this stage. So we can see that the history of karstification started from the Jurassic until the present day now. And one more thing, the Triassic is not exposed, but we know it from the surrounding countries that it is limestone and gypsum and carbonates and salts. So probably there is more karstification that happened in that, but we don't have exposure there. So basically, this is it. Topography, climate, and geology, which dictates what why Lebanon is rich in caves. So we can move to the second one. So again, Lebanon with this karstic exposure, we have more than 5,050 springs, and 40% of them, although 40% of them are karstic springs, which are around 20,000, but they give the most. We know that they discharge the most water, and 80% of the resources come from those karstic springs. So this is a small guide or classification of those karstic springs. The first attempt was done by the UNDP in 1969. The second attempt was in the 80s, and the last attempt was in the 2014. But they classified all of those springs. What I tried to classify is only the karstic springs, mainly because of from their discharge and their structural setting, to define if there is static and dynamic reserves for future use. So let me start directly. There are type 1, and type 1 is basically drainage. So you don't have any barrier, it's only draining the karstic aquifer here. While type 2, there is drainage and the lower barrier such as a mar layer or a seam of clay or something. And then there's more complicated, which is a combination between structural setting and stratigraphic setting, and those are type 2 and type 3. These have, type 3, and these they don't have major static reserves. That's why you can't tap into them. This is why the reason we are classifying them. So again, type 3 is more structural and stratigraphic barriers. Now we move to type 4. It is a drainage spring, but still you have the recharge from porous media or any other type of media that is also affecting those springs. And you can see those sometimes in the discharge graphs that when you look at. Type 7 is again drainage with an overflow. So you have a bit of static reserves, but it is structurally controlled. And in this case, the structure control is a fault, while in the other case is still a fault, but there's a syncline associated with that. There is some static reserves there, but not as much. We move to type 8, which has a frontal barrier, and there's a lot of static reserves there. So there's the flexure along the coast or any other place, and then you have the outflow from the string or the overflow. While in here you have a pull-apart basin. As I mentioned, there's the major Dead Sea transform fault and passing through that area, and you have a lot of pull-apart basins, and you have springs associated with those pull-apart basins and some small lakes associated with them, and that's why you have this type of spring here. While this is similar to type similar to type 8, but it has this one similar to type 8, but it's discharging from a porous media actually. And finally, the artesian springs, which are along the coast, well known in the Mediterranean. This one type 11, and then type 10 is an artesian, semi-artesian spring. Still you have static reserve, but you have frontal barrier, lower barrier, and discharge from a fault in this case. And if you have any questions, you're not supposed to ask.
Thank you for that wonderful tour, Issam. Luke Anderson is up, and Rakam Tamang is on deck.
Hello, everyone. My name is Luke Anderson, and I'm here presenting on behalf of my company, Invenergy, a large developer of renewable energy. And I'm here to discuss our problem with those in the audience who are interested in better developing an understanding of how to responsibly co-locate solar energy facilities on top of karstic landforms across the United States. For those who are not well aware with solar construction, typically our foundations are standard wide flange I-beams that are driven into the ground anywhere from 5 to 15 feet. These piles are then spaced approximately every 25 feet on a grid pattern. We attach that to our racking system and then the solar panels. The foundation systems might be considered rather small compared to a building, but these utility scale solar projects are sometimes over 1,000 acres and 20,000 piles for a site. Furthermore, the site may require grading, removing the topsoil, and altering the hydrology. So again, solar projects are being built at utility scale across the entire country, and certain regions have a higher concentration of karst landscapes. That's why kind of we're all here. Identifying karst with survey and subsurface investigations is underway on many project sites to provide a general understanding of the risk and the distribution of these features, but the next steps are not as well constrained. The reality is that it is not financially reasonable or feasible to find every karst feature, and the industry is really looking for a way to use the limited information that we can collect with surveys and investigations in conjunction with regional data to generate a decision about whether to proceed into construction or to simply cut and run because it's just too risky. So without a specific way to quantify the risk right now, managing it is the best available option that we have. Remediation methods can be completed during construction if sinkholes develop. Stormwater management plans are put in place to reduce that karst-water relationship risk. And avoidance is the best strategy that we have. And major features that are identified in the survey stage are removed from the buildable acreage altogether. However, we know that an unknown number of features will still be there regardless. Alternate foundation systems are an option that minimize the ground impact and they preserve the in situ soil and hydrology conditions, but these are at a premium compared to the traditional I-beam that's being deployed all over the country. So while mitigation is necessary and helpful, these ideas need to be further built on in addition to improving our risk quantification before going into construction. Our industry knows how to identify these landforms and find some specific features with our surveys and investigations. Now we want to improve the gap between knowing the karst landform and moving into construction. There are a number of things that this could be related to that we're interested in looking for. Active research projects on construction sites where you are doing groundwater monitoring or sinkhole monitoring. Continuing to improve a statistical understanding of the risk and something akin to seismic or flooding concerns. And I've actually heard a number of things at this conference that I've found fascinating, the things that are going on in Ohio with their database, the machine tools, machine learning, and the sinkhole susceptibility index. I think the USGS is developing all awesome ideas that we're really interested in learning more about. Our company understands that karst is a team sport, and we are looking for members to join our team and help us as we continue to move towards a clean energy future. So thank you all, and please get in contact with me or others from the Invenergy team are in the back corner if you would like to run some ideas by us.
Thank you, Luke. Rakam is coming up now. Ira is on deck, and I'm just going to pre-warn David O'Brien that you're after Ira.
Thank you all. I'll be talking about today about the sinkhole susceptibility mapping using the machine learning tools. I'll be focusing on machine learning. So sinkhole hazard, like we have been talking a lot, we have been hearing a lot of lectures past 3 days. I'm going to be going in detail this one. So sinkhole maps, we can find a nation scale sinkhole map, USGS map, state scale. There are a couple of, like every states have a single maps. And then Karst mapping tools, we have been hearing a lot of lectures in past 3 days, GIS, LiDAR, INSAR, machine learning tools. I'll be focusing on machine learning tools. So machine learning, it is a branch of artificial intelligence. So basically you can classify into 3 categories: supervised, unsupervised, and reinforcement learning. So in the Karst issue, Karst susceptibility mapping, mainly supervised machine learning tools are used. So they are like ANN, Bayesian, and then logistic regression, and support vector machine, random forest, decision tree. These are used in the real world, like Amazon, YouTube. They have been like using this machine learning tool. For example, Amazon, to give the what's based on the past purchase history, what could be the like customer may be interested in. For YouTube, similarly, like based on the past history of the past watch history, like recommend like what type of the video they may be interested in. They have been using, but in terms of our Karst or geotechnical engineering or civil engineering problem, we have to be really careful because risks associated and liability because of that, like we have a big risks and liabilities. We have to be careful before using these tools. These have great like benefit to solve for the classification regression, non-linear classification regression problems, but it has certain demerits. I'll be talking about that. So in terms of the sinkhole susceptibility mapping, there has been like numerous research paper, could be 15-20 papers all around the world, United States and several parts of the world we can find. Basically what they are doing is they have a non-sinkhole and then sinkhole contributing factor. Correlate the sinkhole contributing factor to develop a model that can classify whether there is a real sinkhole or a false sinkhole. That has been done. Basically, they are looking geometrical features like LiDAR derived depressions, compactness, depth index, and geological features and hydrogeological features, and then ground movement. So with the traditional machine learning tools, there are like some issues. So the one of the issues is like it can develop a model, it can predict, but it does not say like how it come up with that. That's the real challenge for engineers and geologists, because without knowing like how they are doing using in the real world problem, that's a problem. And then another big issue is generating the same results, and when they train frequently, repeating the training process, sometimes deep learning model, like they will not produce the same model and results can be like variable. So these are the problem with the traditional machine learning models. So, but good news is there has been some like great research advancement, like a probabilistic neural network, Bayesian neural network. It can give like reliability in terms of data set and uncertainty in terms of data set that can be used. And another main thing we can do is like all of these researches, they are focused on particular set. Either they are looking geometrical parameter, or they are looking geological only, or like hydrogeological, but there is not a comprehensive model that account entire like contributing factor. I think what we can do is we can incorporate all these sinkhole contributing factor and develop a sinkhole prediction models. That will be the good idea. I'm looking for a data. If anyone has good data set, I'm really happy to collaborate. Thank you.
Thank you very much, Rakam. Ira's up and David O'Brien's on deck. I'm here today to ask for your help because I've been studying caves and karst and sinkholes for 50 years, and the further I get into it, the less I'm understanding what a sinkhole really is. So I'm going to put together a poll that will be sent out over the internet via email and stuff that people can give opinions, because I want to hear people's opinions. But I'm going to ask some of your opinions today. You may have had the experience of talking to clients or to students about closed depressions, whether they're sinkholes or not, you know, how they fit in, how they occur. There's a lot of different reasons why we might want to define actually what a sinkhole is. Clarity amongst ourselves, clarity communicating to the public, and that's a real problem, and particularly for legal proceedings. And a lot of the problems that I've had is in expert testimony cases where we're going back and forth and say, well, what is a sinkhole? What isn't a sinkhole? What's the different terminologies that we use? So here's some questions for you. Is a sinkhole that has been filled, you know, flat, is it still a sinkhole? So if you think yes, can you raise your hand? About half the people, okay? What about a shaft like Sotno de Golondrinas or a big pit? Is that a sinkhole? Raise your hand if you think yes. Fewer people, and they're not raising their hands as far. Are sinkholes and dolines the same things? About a third of the room. Is a swallet or a panur, is that a sinkhole? Okay. How about a polya? Is that a sinkhole? The Slovenians had to leave, unfortunately. I'm sure they'd weigh in on this. Some people are saying yes. Can a sinkhole ever be in a non-karst setting? Raise your hand. A lot of agreement on this. Okay, I'm surprised, but pleasantly surprised. So here's two things which are called sinkholes, one of which is on the cover of a previous proceeding. This is a collapse into an inactive phosphogypsum stack, and this is a collapse on a street in downtown Cleveland that happened last week. Okay. This one happens to be in a limestone area. This one's in a shale area. The one on the left, would you call it a sinkhole? Raise your hand if yes. How about the one on the right? Is it a sinkhole? Okay. So I've been sort of rolling over my head, what are some things we can agree on? So to me, a sinkhole is a landform, kind of like a hill or a valley or a mountain. Raise your hand if you would say a sinkhole is a landform. A lot of agreement. I'd also argue that it's a genetic term, not solely morphological. Right? So for an extreme example, suppose we had a meteorite impact in a carbonate area, and there's a closed depression there. So it's a closed depression in limestone, but it formed from meteorite impact. Is that a sinkhole? All right. And then finally, I think we confuse the public by confounding a thing and an event. If we say a sinkhole happened, that's the same as saying a mountain happened, okay, which you wouldn't say. We could say a sinkhole developed, okay, and I think it's a better way because it really explains what's going on. So just quickly, I've got three definitions here. This one's from the Glossary of Geology. It has nothing about the genesis of the feature. Okay. It doesn't say anything about the genesis. This is one from the Lexicon of Cave and Karst Terminology. Again, it doesn't say anything about the genesis. Thank you. And then finally, This is the one from the Oxford English Dictionary. It's the only one that talks about the genesis, and I think it's actually the best definition of the three that I looked at. So anyway, I'm out of time. Send me questions that you think I should put into this poll. I'm going to take the poll, get as many people as we can, and then we'll distribute the results and learn something about what we think about sinkholes. Thank you.
You just clip this where it's comfortable.
Okay. I'm with you. Well, good morning, everyone. We only got 5 minutes, so I'm going to keep this quick. I usually start off with a joke, but I won't today, so I'll just say that I grew up in northern Alabama, so I have a real strong accent, and you'll figure out by the end of the story that that's not true, so I don't sound like I'm from Alabama. Also, I usually tell a talk about how I'm on Canada's top 10 most wanted list. Don't have time for that. Stop by the booth and ask me. It's a true story. All right, so we're going to talk about UAV LiDAR today. So UAV is an unmanned aerial vehicle. We've been doing LiDAR from UAVs for 7 years now. The top one on the left is a DJI 600. Most of you know how big that is. The one below is a Harris H6, and that is actually a hybrid drone that has a gas-electric engine that powers a generator, that powers batteries, and it sounds like a flying weed whacker. No kidding. You will not miss this thing in the air. It's loud. It's very heavy. It's carrying a Regal Vux sensor, which is $250,000, so it's very expensive. The first one we bought 6 years ago was about $150,000. There's a close-up, so if you look at it real close, you can see the generator motor there and the Vux and the size of it. It flies about 80 minutes. So the DJI 600 flies about 20 minutes. And so the difference between 80 and 20 is a lot of extra process. And every mission you have to fly, every mission you fly, you have to calibrate and do processing. If you can stay up 80 minutes, you can fly a couple hundred acres in 80 minutes. That's our Harris HX8. That's a much bigger drone. That's a battery-operated drone, which flies about 30 minutes, but that thing carries that payload. The Vux weighs about 11 pounds, and it carries that very easily. I like to point out that this is the LiDAR sensor. This is an IMU on the back of it, and GPS. If you don't know what an IMU is, I'm willing to bet that everybody in this room has an IMU on them. Your iPhone has an accelerometer in it, measures the motion when you move it. So that's how they're doing LiDAR on an iPhone now, because it's knowing the orientation. So everything that's mapping, moving, and if it's outside, it has GPS, and it has an inertial measurement unit, and it's measuring the heave, pitch, and roll of that bird as it flies through the air. Some of our early LiDAR, you can see just intensity values. That's obviously a mine site. You can obviously see the piles of material, lime rock or sand probably. You can see it actually picks up paint on it because of intensity values, the return that it gets. So you can map a lot with it. I always like to show, we do a lot of power line mapping. You can see that the LiDAR, the Vux, the big one, the expensive one, picks up power lines really easily, and we can fly at the maximum height of 400 feet. So you can really pick up a lot of detail with the Vux. There's a lot of misinformation about LiDAR. We have LiDAR really dialed in to the same accuracy as GPS, plus or minus a tenth of a foot if we're doing surveying. And so you can get really high accurate LiDAR, survey grade. You just have to know what you're doing with processing. And you can filter off the vegetation, that can disappear, and you can have bare earth. Same thing, you can see the actual error values, 300s, 400s, very accurate when we're doing our check shots. I always like to show this. This is very heavily vegetated. Then we filter off the vegetation, the open area. You can see the density of LiDAR here. Even after filtering off all the vegetation, you see how many points you have to create that bare earth model. You're going to see every little depression, every little nook and cranny. LiDAR on drones does not like water. You've all heard about bathymetric LiDAR now? Well, that's a $4 or $5 million sensor that goes in the airplane. And so you're not putting that on a drone yet. That's probably coming in the future, but right now, LiDAR on drones doesn't like water. As a surveyor, I always ask, well, how do you know you're really on the ground? And this is the one thing about UAV LiDAR that really surpasses the airplane. You can get upwards of 200 points a square meter. And so when you filter off vegetation, you're still left with 40 or 50 points a square meter. And when you compare those points, they're either this thick or they're this thick. And if they're this thick, you know that your data is really good because they're all laying side by side. If the data's thick, my guys will say, Dave, the data's no good in this area. And it typically is good unless it's palmettos or very tall, thick grass. some more power line map. And you can see, we colorized the cloud on this. Everybody gets excited about that on LinkedIn. As a surveyor, it's kind of meaningless. And so some bridge work we did. Everything underwater is not LiDAR. That's multi-beam. That's a whole other talk, so I'm not going to talk about that. But this is all LiDAR data. We did a whole corridor there. You can actually see, that's another view of the bridge. You can actually see the piers don't come out underneath. You're losing data here and here because they're obstructed. We do a lot of work for the Army Corps of Engineers. Took me a long time to convince them to use a drone, but they love it now. These are the rocks on some jetties. They're rebuilding the jetties. It's very accurate. This is one of our most famous sites. Way back, geez, it must be 2017 or 18 now. The Orville Dam busted. I think you all remember that. And that's the spillway. It's very steep. We mobed out there in 24 hours and flew LiDAR on that, delivered the data the same day, and allowed them to calculate what they were missing, basically. And they were also doing bathymetry on the lake down below that was caused because of it. Yeah, that's what it looked like. We used it on a bird sanctuary, couldn't put boots on the ground, and surveyed out in Oregon. So anywhere you can't put people, we put the control on shore and just flew the drone over the island. Very good with vegetation being removed. If I could get this right. You can, oh, my hands are too big. Well, I'm sorry, I've messed it up now. But you can see that the vegetation removed, you can see the lines and everything on that. So that's pretty much my talk today. You can see an image versus LiDAR, and you can see the comparison. You can see the trucks and vehicles filtered out. So thank you, everyone. I appreciate your time.
Thank you, David. Great stuff. Our final Karst clip of the morning is a recent addition, Dan Doctor, after which we'll have our lunch break.
Thanks, everybody. With some apologies to our international colleagues, this talk is going to be focused on the United States. And I will say at the outset that I'm presenting this non-technical presentation as a citizen of the United States and not a representative of the U.S. Geological Survey or the federal government. So all opinions are my own, not those of the federal government. How many of you are aware of the Supreme Court decision in 2020 with respect to the Clean Water Act? Raise your hand. Just a handful, maybe 2% of the room. Okay, so that's why I want to give this presentation, because I think this decision has pretty profound implications for karst research moving forward and legal cases. The Clean Water Case of the Century, this is a website from Earth Justice. Earth Justice is an organization that provides legal services to fight court cases having to do with environmental issues. And in the image here, you're seeing a beach and a sea turtle off the coast of Maui, Hawaii. And the case really dealt with injection of wastewater that the county was doing near the coastline, treated wastewater that was making its way into the ocean and degrading the coral reef and the environment along the coast. That was a fairly popular snorkeling site, a tourist destination. And they were injecting millions of gallons of treated sewage into the water in lava flows. So this is pseudokarst. The location was there on the island of Maui. And the citizens there were complaining about this because there was degradation, there was algal blooms, and the county didn't really respond. And so the citizen groups, including Hawaii Wildlife Fund, Sierra Club, Maui Group, Surf Rider Foundation, and the West Maui Preservation Association, they used the services of Earth Justice to bring this lawsuit against the county. In the course of that, they did a dye trace investigation with people from the University of Hawaii, and here are the folks. Craig Glenn, was the principal investigator on this, just going to blow up their dye trace study work. So basically, they put dye into the injection wells of the wastewater and traced it into some seeps and springs that were coming out in the shallow marine environment. There are two major spring groups, and these are the breakthrough curves. And it's kind of hard to see, but they've got the time of first arrival was about 84 days for both of them. The peak concentrations were coming through about 9 to 10 months later, and the mean transit time on the order of 14 to 16 months. So it's a pretty long-lived dye trace for many of us in Karst. So how far did they go? Well, they only went about half a mile. So this is the area of the injection wells here on the coast. The springs are here. And, you know, it's a dye trace that took 84 days for the first recovery. It only went half a mile, but there's a greater plume, and they modeled this around these injection wells. The point is that they dye traced it. That's the point. And what did the Supreme Court say? The Supreme Court says that if there is a pollutant that discharges to navigable waters, including the coastline, through groundwater from a point source, that point source requires a permit from the Environmental Protection Agency. And their term was that the movement of pollutants through the groundwater is the functional equivalent of a direct discharge from a point source into a navigable water. In other words, you know, it's basically Karst. This applies directly to a lot of what we do in Karst. And you can read the law. I'm not going to go through it too much, but I don't have a lot of time. Thanks. If Ira will let me, you might. Think about this. The EPA calls a discharge of non-hazardous fluids underground can be classified as a Class 5 injection well, which under the terms of the Supreme Court decision definitely qualifies as a point source. So any discharges of stormwater, let's say, that are directed into a sinkhole could be classified by the EPA as a Class 5 injection well, and therefore would require a permit from the EPA to have that kind of discharge occur. This brought to mind a dye trace that I had been involved with over a decade ago, where there was a sinking stream that was, we hypothesized was going to two springs over here, one of which, Face Spring, had been a public water supply for the city of Winchester, Virginia, and had been taken offline because it was known to be under the influence of surface water, but they didn't know where the surface water was getting to the spring, so we did the dye trace to try to determine it. Really was a fairly straightforward trace of about a distance of a couple kilometers, but there was a lot of road runoff in an industrial complex. Sorry, let me back up. Industrial complex up here, and they had routed a lot of stormwater off of their site into this natural drainage, but they had improved it to some degree. And in the course of doing that, of course, it all ran down this swale into a sinkhole here. So this was after a storm event. Normally it was dry, but after the storm event, it all went there, and it went to this spring, which, as I said, used to be part of the city's water supply and was taken offline. So we did the dye trace. This was many years ago. I published this. A pretty quick breakthrough curve, about 48 hours after the dye was injected, and it continued to seep out through the system over time. The point is not to describe the results of the trace, just the fact that when we did this, the question was, would this feature require a permit from the EPA? In other words, would, in the process of directing that stormwater runoff to this sinkhole, invoke a permit from the EPA? And I guess that's just the question. Does road or ag runoff flowing into a sinkhole that has been traced to a surface stream require a permit from the EPA? And I'll leave it to your imaginations to think about the consequences of this Supreme Court decision. Thank you very much.
Thank you, Dan, and thanks to all of our speakers, and especially thank you all for keeping on time. I appreciate it.